a little bit summary. So we last week we learned about clock and timestamp. Okay, and for normal people, it seems that clock or daily or calendar is work very fine because the exceptional case is a very little. For example, like the leap year is happen every 4 years, something like that. And then for the lunar calendar, for example, like 1 month there is a 30 day or 28 day or 29 day or 31 day. No one care about it, okay? Because people think that okay, 28, 29 or 30 or 31 is not really a big deal, okay? But when it comes to a second, because even the second people don't care, but for computer science, for system, we care about it because the computing power is very fast. So we count it in, like, for example, like microsecond or nanosecond, something like that. So if the time is running a little bit slow, for example, like if we browse a website or running an application, if an application is running, for example, like 5 seconds or 10 seconds slow, we are boring. Okay, the user don't happy with it. That's why we said that the system is not user friendly. And sometimes when the system is not responding, sometimes the request is running out of time. We call it time out, something like that. People are not happy with it. Okay, so computer science really take the time very seriously. And then there's also a problem with the time, as we have learned last week, that the time is not accurate. No matter how good the technology is, people trying to find a good technology in order to measure the time. But even those time are not very 100% accurate. That's why there's always some error. Okay, so the little error, those error, we call it a clock drift or clock skew, something like that. So clock drift is the increasing of the error gradually. For example, like from small to bigger and bigger and bigger, something like that. We call it clock drift. But if there is a two clock or two or three or whatever clock within the same time, they show different time. So that we call clock skew. For example, like one clock showing 1 o'clock, another clock showing 1 o'clock and 1 minute, something like that. So that we call a clock skew. Okay. So that's why when we want to work with clock, we need to rely on some clock that are very accurate. So those clock we call it atomic clock. So atomic clock is the clock that very the most accurate one, and the other one is less accurate. That's why we have also the NTP server, the network time protocol server, that using atomic clock in order to measure the time. So whenever the client would like to know what time is it, they usually request to those kind of server, okay? And those server will respond what time is it. And there are three ways that we need to reset our clock. For example, like if the client and server has a very large clock skew, we have three kind of step to do. So anybody know what are those steps? For example, like client and server, now the time is different. So what will the computer or operating system react to those error? ចឹងបើសិនជានិយាយខ្មែរឡើងវិញយើងដឹងថាពេលវេលាហើយអីហ្នឹងបើសិនយើងនិយាយជានេះឡើងវិញមានន័យថាបើសិនជាមនុស្សយើងគិតថាម៉ោងអីអីវាអត់សូវជាបញ្ហាចោលទេតោះនៅឧទាហរណ៍ថាក្នុងមួយថ្ងៃមួយខែមាន30ថ្ងៃ28ថ្ងៃ29ថ្ងៃអីយើងគិតថាធម្មតាព្រោះវាអត់មានអីប្រែប្រួលមួយថ្ងៃខុសមួយថ្ងៃពីរថ្ងៃអញ្ចឹងយល់ទេតទៅពេលមួយឆ្នាំតឡើងតែមួយថ្ងៃឧទាហរណ៍ថាឆ្នាំមកគ្រប់ហ្នឹងវាមាន366ថ្ងៃអញ្ចឹងយើងថែមថ្ងៃ29ខែ2ហ្នឹងក៏វាអត់មានអីបញ្ហាព្រោះ4ឆ្នាំអីបានវាកើតឡើងម្ដងអញ្ចឹងយើងអត់សូវតាក់ទង care ជាមួយនឹងបញ្ហាអស់ហ្នឹងឯងក៏តែនៅក្នុង computer science គឺដោយសារតែយើងអត់មានគិតរឿងអាម៉ោងឆ្ងាយអញ្ចឹងឯងដោយសារ processing វាដើរលឿន CPU ហ្នឹងវាដើរលឿនអញ្ចឹងពេលដែលគេនិយាយរឿងម៉ោងពេលវេលាគេអត់និយាយដល់ថ្ងៃដល់ខែដល់ឆ្នាំគេនិយាយរឿងវិនាទី milli វិនាទីឬមួយក៏ nano វិនាទី micro វិនាទីអញ្ចឹងទៅអញ្ចឹងតទៅពេលអញ្ចឹងបានន័យថាខុសម៉ោងតែតិចតួចហ្នឹងក៏អាចធ្វើឲ្យ system យើងមានបញ្ហាដែរហើយជាពិសេសការបង្កើតម៉ោងរបស់មនុស្សយើងហ្នឹងគឺតាំងពីប្រវត្តិសាស្ត្រមកអត់មានណាគេបង្កើតម៉ោងមួយដែល accurate 100%ទេaccurate ជាងគេគឺ atomic clock ហ្នឹងហើយបានន័យថាហ្នឹងគឺ accurate ជាងគេហើយក៏តែសំបីតែ atomic clock ហ្នឹងក៏វានៅមានលំអៀងដែរហើយចុះតម្រាំតែ technology ដែលអត់ប្រើ atomic clock ហ្នឹងគឺវាកាន់តែមានភាពលំអៀងទៀតហើយតោះណាមូលហេតុហ្នឹងហើយបានវាកើតចេញជាបញ្ហាពីរដែលយើងហៅថា clock drift ឬមួយក៏ clock skew ហ្នឹងមានន័យថាអា clock drift ហ្នឹងគឺម៉ោងអា error ហ្នឹងកាន់តែធំទៅតទៅពេលអា clock skew មានន័យថាបើយើងយកម៉ោងឬមួយក៏អានាឡិកា2យកមកមើលក្នុងពេលតែមួយនាឡិកា2ហ្នឹងវាខុសគ្នាអាភាពខុសគ្នាហ្នឹងហើយដែលយើងហៅថា clock skew អូខេហើយចឹងទៅ client គឺត្រូវ rely on អាណាមួយដែល accurate ចឹងវា rely on server ដែលយើងហៅថា network time server ហ្នឹង network time protocol server ហ្នឹងគឺវាទាញម៉ោងពី server ហ្នឹងមកវិញបើសិនជាយើង connect ទៅកាន់ internet ហើយមួយទៀតបើសិនជា client ហើយ server ហ្នឹងវាម៉ោងវាខុសគ្នាឆ្ងាយពេកវាមាន3ដំណាក់កាលដែលយើងត្រូវដោះស្រាយដែល operating system រួមមួយក៏មនុស្សត្រូវការដោះស្រាយអញ្ចឹងមានណាគេដែលចាំអត់ថាតើនៅពេលដែល client ហើយ server ម៉ោងខុសគ្នាអញ្ចឹងតើអា operating system វា react យ៉ាងណាមានណាគេនៅចាំអត់ So the question is when the client computer and the server computer time are different. So how does operating system or human react to those error? Anybody can answer this question. We know that the time is not accurate, so two computer like a client and server or client may have different time. And then when the time is gradually increasing error, so how do the operating system solve those problems? Anybody still remember? Panet can answer the question. If the client computer and the server computer clock error different and not the time is not the same, so how do the operating system react to those kind of different? Panet nữa Panet. Panet. Kimheng, can you answer the question? Hello, where is everyone? Patana oi.
សំណួរម្ដងទៀត
សំណួរសួរថានៅពេលដែល client ហើយ server ម៉ោងវាអត់ដូចគ្នាបានន័យថាម៉ោងអា server ហើយអា client ហ្នឹងវាកាន់តែអត់ដូចគ្នាទៅវា error កាន់តែឆ្ងាយទៅសួរថាតើ operating system ហ្នឹងវាដោះស្រាយមិនវាមាន3វិធីសាស្ត្រដែលដោះស្រាយនៅចាំអត់3វិធីហ្នឹងឧទាហរណ៍ client ម៉ោង1 server ម៉ោង1នាទីដល់ពេលយូរទៅ1 2នាទី1 3នាទី1 4នាទីអញ្ចឹងណាកាន់តែធំទៅអញ្ចឹងណាអញ្ចឹងសួរថាតើអា operating system នោះវាត្រូវដោះស្រាយយ៉ាងម៉េចនៅពេលដែលម៉ោងវាកាន់តែ error ធំទៅអញ្ចឹង
អត់ចាំហ្មងគ្រូ
មានណាគេចាំអត់ឥឡូវ
គ្រូអាហ្នឹងទី1ដូចជាយើងត្រូវ estimate clock screw
ហ្នឹងហើយ
បាទបន្ទាប់មកយើងយកវាទៅ compare បើសិនជាវាដូចជាតូចជាង125ខ្ញុំអត់ចាំខ្នាត
25 millisecond
បាទ125 millisecond អាហ្នឹងដូចជាកុំព្យូទ័រវាអាច up and slow ខ្លួនឯង
អូខេ
ដល់ពេលដែល clock step វិញអាហ្នឹងដូចជាចន្លោះ125 millisecond វាធំជាង125និងតូចជាង1000អាហ្នឹងតម្រូវឲ្យដូចជា user ហ្នឹងគាត់ត្រូវទៅកែខ្លួនឯងហើយមួយទៀតដូចជាpanic ហ្នឹងដូចជាអាហ្នឹងដូចជា VR ឬហើយវាអត់ធ្វើអីសោះតែម្ដង
អូខេ
ទី3ហ្នឹងខ្ញុំអត់សូវច្បាស់ឲ្យលោកគ្រូ
ត្រូវបានតាទី1ឯងច្រឡំមកទី2ហើយណាទី3 Okay, so the answer is correct, but you only correct the first one, but the second one and the third one you confuse it. Okay, so normally when there is an error, for sure we calculate the clock skew. Okay, clock skew. For example, like how big the error is. Okay, clock skew between client computer and server computer and server. Okay. So if the clock skew, for example, the error we said the letter E. Okay, so if E is less than 155 millisecond, the operating system normally they control the hardware. Okay, so the operating system will speed up or slow down depend on the clock. For example, if the clock is very slow, it speed up a little bit. But if the clock is very fast, it slow down a little bit. Okay, for example, like if it's slow, it slow down the speed. The unit is, for example, like 550 ppm. So if it speed up and speed down like this, so within 5 minutes later, those clock will be in sync. In sync means synchronized. Okay, in sync. So so those are the very little error. Okay, so if the error is very little, the clock will speed up or slow down a little bit in order to adjust for the two clock to be the same. Okay. But if the second level, if the error is more than 155, okay, but it is less than 1000. So in that case, the clock need to be reset, but it is not reset by human. It is reset by the operating system. Okay, not human. So it will reset to the one who are correct. Normally, the server, we trust on the server. Okay, so the client will reset the clock to the server. But for the third step, the error is, for example, is too much. For example, like bigger than 100 seconds. So in those cases, it come to a panic state. So normally the operating system, it do nothing. Okay, so normally OS do nothing. It rely on human to do. Okay, so human need to do the manual work. Okay, so normally the system will not react anything, and then the human need to go to correct the clock and need to see if the client clock is error or the server clock is error, because the difference is too much. Okay, so if you see our lesson next, we will see that here the first step we call slew. Slew mean speed up or slow down the speed. Step mean reset the clock, and then panic mean the human will go to solve the problem. Okay, so we need to review the lesson, otherwise you will forget. You will remember a little bit, but you are not sure. So when you answer, for example, like if I give you 10 points, you only get 25 points, something like that. Okay, so need to review the lesson. អញ្ចឹងមានន័យថានៅពេលដែលម៉ោងម៉ាស៊ីនពីរវាខុសគ្នាអាហ្នឹងគឺធម្មតាម៉ោងគឺមនុស្សភាគច្រើនកុំព្យូទ័រវាធ្វើស្អីៗវាអូតូម៉ាទិកទេដោយសារយើងមាន operating system វាអ្នក handle អាការងារអស់ហ្នឹងអញ្ចឹងនៅពេលដែល error ម៉ោង error ហ្នឹងវានៅតូចបានន័យថាវាតូចជាង125វិនាទីយើងហៅថាវា slow ហ្នឹងមានន័យថាម៉េចអា system ហ្នឹងវាចេះធ្វើឲ្យអាម៉ោងហ្នឹងវា speed up ឬមួយក៏ slow down ក៏ប៉ុន្តែយើងអត់ដឹងទេដោយសារអីវា speed up តិចមួយនៅឧទាហរណ៍ថា550 ppm ហ្នឹងយើងអត់ដឹងថាវា speed up ប៉ុណ្ណាទេតោះនេះក៏ប៉ុន្តែ5នាទីក្រោយមកអាម៉ោងហ្នឹងគឺវាមើលទៅវាទន្ទឹមគ្នាវិញតោះណាបានន័យថាវារៀងគៀកស្មើគ្នាវិញហើយអាហ្នឹងគឺអា step ដំបូងដោយសារតែ error ហ្នឹងវាតិចតួចពេកអញ្ចឹងវាត្រូវការ speed up ហ្នឹងវាមិនមែន speed up ភ្លឹបវាផ្លោះម៉ោងទៅហ្មងឯងបានន័យថាវាធ្វើឲ្យលបឿនម៉ោងហ្នឹងលឿនជាងមុនឬមកក៏យឺតជាងមុនបន្តិចទៅតែតទៅពេល5នាទីក្រោយមកគឺវាសាំងប្រណៃបានន័យថាវាដូចគ្នាតទៅពេលអាទី2មានន័យថា error ហ្នឹងវារៀងល្មមមិនវាធំគួរសមដែរវានៅចន្លោះពី125ទៅ1000 millisecond ហ្នឹងអញ្ចឹងគឺដោយសារតែវានៅឆ្ងាយពេកវា speed up បើសិនជាឲ្យវា speed up ឬមួយក៏ slow down វាត្រូវស៊ីពេលច្រើនជាង5នាទីវាអាចកន្លះម៉ោងឬមួយអីទៅអញ្ចឹងគេខ្ជិលគេ reset បដ ாய் ទៅមានន័យថាឲ្យអា system ហ្នឹងវា reset ម៉ោងទៅកាន់អាមួយដែលវាត្រូវបដ ாய் ទៅតោះណាហើយអាមួយដែលត្រូវហ្នឹងគឺភាគច្រើន server ដោយសារ server វាមិនមែនមានតែមួយ server វាមានច្រើនអញ្ចឹងគេយក average per server មកយក reset មកឲ្យ client បដ ாய் តទៅពេលអាចុងក្រោយគេមានន័យថា error ហ្នឹងវាធំពេករហូតដល់ថ្នាក់មនុស្សសំបីតែមនុស្សក៏អត់ដឹងថា error មកពី client ឬមួយក៏មកពី server ដែរអញ្ចឹងពេលហ្នឹងគឺឲ្យមនុស្សទៅមើលវិញមកថាតើអា clock ហ្នឹង error ដោយសារអីដោយសារ client ឬមួយក៏ server ហើយមនុស្សទៅ reset ខ្លួនឯងហ្មងបើសិន error នៅលើ server reset server បើ error នៅលើ client reset client តោះណាតទៅពេលហើយអា NTP protocol ហ្នឹងវាចេះ communicate យកម៉ោងយកអីមកខ្លួនវាវិញហើយអូខេ understand so if there is an error we have 3 steps to solve: adjust the speed, reset the speed, and human operation to solve the problem. Okay, and the last thing that we learned last week is about time of the day clock and monotonic clock. So anybody still remember this clock? Like what are the epoch time and then the monotonic time? So what are the difference between those two time? មានណាគេនៅចាំ
epoch time ហ្នឹងដូចជាចំនួន second ដែលយើងរាប់ពីការចាប់ផ្ដើមបង្កើតកុំព្យូទ័រលោកគ្រូហ្នឹងហើយចំពោះ monotonic ហ្នឹងអាហ្នឹងពេលដែលយើង start ម៉ាស៊ីនកុំព្យូទ័រយើង
អូខេតែអាបង្កើតកុំព្យូទ័រមិនដឹងបង្កើតកុំព្យូទ័រឬមួយក៏មិនមែនណាពួកអីអាកុំព្យូទ័រនោះវាអាចបង្កើតមុន1970អញ្ចឹងបានន័យថាគឺពេលដែលគេចាប់ផ្ដើម count វិនាទីនៅឆ្នាំ1970អូខេ Okay, so let Arthur, can you explain the difference between epoch time and monotonic time? Hello, Arthur Potrel, can you explain the difference between epoch time and monotonic time? What are the difference?
Hi.
Yeah.
Hi.
Yeah. Can you answer this question? What are the difference between epoch time and monotonic time?
Epoch time is the time that starts from the 1st January on 1970.
Yeah.
On millisecond.
Yeah.
And what is the
monotonic time?
I don't remember from monotonic.
Okay, so monotonic time is the time when we start our machine. When we start our machine, it will count, but it is not the real time like today is 2022 like that. So monotonic time is when we start the machine. There is some clock is running, so we use that kind of clock in order to count the time. Okay, but it is not really the calendar time. Okay, so those are monotonic time. Okay, so if you see the lesson in the programming language, we have a different library. So for example, like if you want to use the time of the day or epoch time in Java, there is a method called system.current current time milli. So those are called by using the epoch time. Okay, but if you want to use the monotonic time, the time when your computer start running, when you call system.nano time like that, so that is not the time of the epoch time. Okay, there's no error, something like that. So this time is the computer is starting, and then this is a local time, but this time is could be from the server. Okay, so that is the difference between time of the day. So normally time of the day is the epoch time, and then a monotonic time is the time when your computer is running. Okay, so when we want to compare about the speed of our algorithm, we don't use time of the day or epoch time because it is result in the leap second, the speed up, slow down error, something like that. But when we use a monotonic time or the time in our computer, there is no error. Why? Because we use our local machine. Okay, we want to compare the code, the speed of the code by our local machine. That's why when we want to show the result of our code, for example, like my code is running 5 seconds, something like that, we need to tell about our computer information. For example, like I'm using a Windows operating system. My computer is, for example, like a MacBook or something, for example, like Dell computer with the CPU like this, like that. So that people will know that, oh, when your code is running in those type of machine, the speed is like this. Okay, but it depends when your code is running in the other high speed machine, it will be faster. Okay, but the good way to count the computing time of your algorithm is using the monotonic time. Okay, not the epoch time or time of the day. ចឹងម៉ោងហ្នឹងវាមានពីរប្រភេទណាដូចយើងនិយាយកន្លែងនេះគឺម៉ោងហ្នឹងវាមានពីរប្រភេទទី1យើងឲ្យឈ្មោះថា time of the day ឬមួយក៏ epoch time ហ្នឹងគឺយើងចាប់ផ្ដើមរាប់វាពីឆ្នាំ1970មកខែ1ថ្ងៃ1តោះណាអញ្ចឹងរហូតមកដល់ឥឡូវគឺយើងមើលទៅគឺយើងឃើញវាលេខវាច្រើនហើយអូខេតែអា time មួយហ្នឹងដូចយើងនិយាយអញ្ចឹងមកដោយសារតែ time ហ្នឹងវា error អញ្ចឹងវាមានអា speed up slow down reset ឬមួយក៏អីហ្នឹងទៅអញ្ចឹងបើសិនជាយើងយកអាក្នុងពេលដែលយើងទៅសេវ program ហើយយើងយកអា epoch time ហ្នឹងយកមក count ស្រាប់តែដល់ពេលថ្ងៃណាមួយដែលវា speed up slow down ឬមួយក៏វា reset time វាធ្វើឲ្យ algo អញ្ចឹងវាអត់ត្រឹមត្រូវទេតោះណាអញ្ចឹងដើម្បី compare ថា code របស់យើងហ្នឹងវា run ទៅស៊ីពេលអស់ប្រហែលភាគច្រើនគឺគេអត់ប្រើអា epoch time ឬមួយក៏ time of the day ហ្នឹងទេគឺគេប្រើអា monotonic time វិញអញ្ចឹង monotonic time នោះឈ្មោះវាគ្រាន់តែកលិបទេតែតាមពិតទៅគឺអាម៉ោងរបស់ computer local របស់យើងម៉ាស៊ីនរបស់យើងមួយគ្រឿងហ្នឹងម៉ោងពេលដែលយើងបើក computer មកវាមានអាម៉ោងរាប់ count ទឹកហ្នឹងគឺគេយកអាហ្នឹងយកមករាប់តទៅពេលអញ្ចឹងពេលដែល computer យើងចង់ដឹងថា speed algo របស់យើងហ្នឹងលឿនឬមួយក៏យឺតគឺយើងត្រូវប្រាប់ឈ្មោះម៉ាស៊ីនយើងទៅគេទៀតបានន័យថាខ្ញុំ run នៅលើម៉ាស៊ីន Dell ម៉ាស៊ីន MacBook CPU ខ្ញុំចំនួនប៉ុណ្ណេះតទៅពេលខ្ញុំ run អា algo មួយហ្នឹងទៅវាស៊ីម៉ោងអស់ប៉ុណ្ណេះតើណាតែតទៅពេលយើងយកអា code របស់យើងដដែលហ្នឹងយកទៅ run នៅម៉ាស៊ីនគេផ្សេងទៀតដែលម៉ាស៊ីនគេផ្សេងហ្នឹងវាអត់ដូចយើងទេឧទាហរណ៍ថាម៉ាស៊ីនគេផ្សេងទៀតហ្នឹងវាម៉ាស៊ីនរៀងធំជាងមុនហ្នឹងទៅវា run នៅលើ server លើ cloud អីហ្នឹងទៅអញ្ចឹងពេលហ្នឹងគឺយើងឃើញ speed វាខុសគ្នាដោយសារតែអាម៉ោងយើងគិតពីម៉ោងរបស់ local machine យើងអត់គិតអាម៉ោងរបស់ server តើណាតែអញ្ចឹងវិធីសាស្ត្រដែលល្អសម្រាប់យកមក count ម៉ោងគឺយើងប្រើ monotonic clock យើងអត់ប្រើ epoch time ទេ okay so remember we have two type of clock and whenever you want to write to compare your code remember to use monotonic clock to compare your algorithm but not the time of the day okay and see what in the programming language like Java, Python or whatever what library that we use to call the monotonic clock okay not the time of the day clock. Okay, so let's continue our lesson. We have a few slides more before we go to the next chapter. So normally this is related to the message ordering. So when we have a lot of computer talking to each other, there may be some delay because if it depends on the network cable and the speed of the internet, something like that, there may be the network delay. So when the distributed system want to send a message together, we some of the application will want to know like what message come first. Okay, for example, like in the what we call bidding, in the bidding process. So in the bidding process, we want to know who bid first and with which price. If 2 person bid the same price, those who bid first will be the winner. So in those kind of application, the message ordering is very important. Okay, but if the other application like you chat with somebody and the message of them come later than your chat, it doesn't make a big deal. Okay, so that we call a message ordering problem. For example, like this one, computer 1 or user 1 send a message 1 to both computer like user 2 or user B or user C. So the message arrive here at T2, and then this message arrive here at here. Okay, and then user B also send the message to the user A and user C. So you can see that this message M1 is sent from user 1, is sent from T1, but it arrive on user B first, but it arrive very late on the user C. Okay, but when the user B send the message, so the message M2 is sent from T2, but it arrive first before the message M1. So in this case, there is some delay of the message M1 from user A to user C. Okay, so that is why the message ordering is very important with some application, but some other application it is not very important. Okay, so if there is if the message ordering is important, we need to solve the problem like how do we deal with the message ordering. Okay, ចឹងតាក់ទងជាមួយនឹងការផ្ញើសារបានន័យថាបើសិនជាយើងមានកុំព្យូទ័រតែមួយវាមិនសូវអីទេតទៅពេលនៅក្នុង distributed system កុំព្យូទ័រវាមានច្រើន3ឡើងលើអញ្ចឹងឧទាហរណ៍ថាឥឡូវដូចយើងមើលដល់ message មួយនេះអញ្ចឹងuser A នេះវា send message មួយមកឲ្យអា2នេះតែអា message នេះវាមកដល់ B មុនតែវាក្រទៅដល់អា C នេះវារៀង delay តិចតទៅពេលអា B នេះវា send message 2ទៅតាមពិត message 2ហ្នឹងវា send ក្រោយអា message 1នេះទេព្រោះអា message 1នេះអា user A នេះ send តាំងពី T1 តទៅពេលអា user B នេះ send message 2នេះនៅ T2 ប៉ុន្តែអា message 2ហ្នឹងបែរជាមកដល់មុនអា message 1វិញតោះណាអញ្ចឹងក្នុងករណី application មួយចំនួនវាអត់ជាចោតជាបញ្ហាដូចថាណាគេឆាតមកឃើញអក្សរមុនអក្សរយឺតអីវាមិនសូវចោតជាបញ្ហាតែបើសិនជាតាក់ទងជាមួយនឹងរឿងអា bidding បានន័យថាការប្រកួតប្រជែងគ្នា bidding ចង់បានស្អីមួយគេថាបើសិនជាណាគេ bid មកមុនឈ្នះអញ្ចឹងទៅណាគេ bid យឺតចាញ់អញ្ចឹងទៅតោះណាបើសិនជាយើងធ្លាប់មើលនៅក្នុង online អីពេលខ្លះគេមានការលក់របស់អីសម្រាប់ដេញថ្លៃដេញអីអញ្ចឹងណាគេ send ទៅតទៅពេល send មកអា message ហ្នឹងក្រមកដល់ពេកអញ្ចឹងនាំឲ្យអាម្នាក់ដែល bid មុនហ្នឹង bid តម្លៃទាបក៏តែវាក្រមកដល់ហើយគេ bid តម្លៃខ្ពស់ជាងតែគេមកដល់មុនអញ្ចឹងនាំឲ្យគេឈ្នះហើយអញ្ចឹងណាអញ្ចឹងទៅវាធ្វើឲ្យមានបញ្ហាកើតឡើងតោះណាអញ្ចឹងនៅក្នុង distributed system នៅពេលដែលយើងចង់ធ្វើ application ដែលការ message ordering ហ្នឹងវាសំខាន់គឺយើងត្រូវតែដោះស្រាយបញ្ហាមួយហ្នឹងបានន័យថាតើយើងធ្វើយ៉ាងណាដើម្បីដោះស្រាយដឹងថា message មួយណាមកមុនមួយណាមកក្រោយអូខេ So in summary, in the distributed system, message may be arrive earlier or late depend on the network latency. And remember that some application, this is not a problem, but some application it might cause a very big problem. Like how do we know which message come first and which message come later? Okay. So in that problem, we need to define the ordering of the message. So we call message ordering problem, or we need to define the clock or the time. For example, like what time the message 1 come and what time the message 2 come. Okay, and how do we know that which message come first? So to solve the problem, there is one solution called happen before relation. So happen before relation means it is the relationship between the two events. Okay. So what is an event? An event is something happening at one node and sending or receiving a message or a local execution step. Okay. So for example, like when user 1 sends something to user 2, it is an event. Okay. So when user 1 do something within themselves, it is an event. Okay. So that we call event. And then we depend on those events in order to compute the time. Okay. We say an event A happened before event B, and we can write in the mathematical model like this: A and arrow B, something like that. So A and B occur at the same node, and A occur before B in that node local execution order. So we say that, for example, like this one, maybe the other one. Okay, for example, like A and B. A and B is an event. It happened within the same computer, the same machine. So normally in a network or in distributed system, sometimes we don't call machine. We call it node like this. Okay, okay, NODE. So for example, like this event A and B. So if it happened at the same machine, and we can see that A is happening before B, so we said that A happened before B, and then the relationship we use the arrow like this, and we said that this is a happen before relationship. Okay. Chẳng bạn này tha đập bay đăng tha event na message na mà muốn đưa môi cái ấy tới cứ cái count tới event nó miền này tha mấy cứ chỉประการmỗi đại cao làng bạn này tha bị ai chỉ ca execute na lơ local na machine nó có cái hàng event cả send message bị computer mỗi cái computer mỗi tiết có cái hàng event này toàn này hay relation របស់វានឹងមានន័យថាមិនបើសិនជា A នឹងវាកើតឡើងមុនណា B នេះយើងហៅវាថា A happen before B ហើយយើងដាក់សញ្ញាព្រួយនេះតោះណាហេតុអីបានយើងដឹងថា A នឹងវាកើតមុន B ដោយសារតែវា run នៅលើកុំព្យូទ័រតែមួយអញ្ចឹងបាទអានេះ T1 អានេះ T2 អញ្ចឹងនាំឲ្យអា A នេះវាកើតឡើងមុន B ឯងតោះណាយល់ so happen before relation is a relationship between two events. And event is something that happening. It could be happening locally or sending something to another machine. Okay. So if we said that A is happening before B, that means the event of A is happening before B. Why we know that? Because it is happen at the same machine. We don't talk about the other machine. So if it happen at the same machine, if A happen at T1, B happen at T2, for sure A is happen before B. Okay. Event A is sending some message M, and event B is receiving of the message M. So assuming that the send message are unique. So for example, like in the case of between two computers now, so now we don't talk about one computer, we talk about two computers. So if we have two computers, one is sending message and another one is receiving message. For example, like and even B is sending a message M1 and even C is receiving a message M1. So we say that B is happen before C. Okay, because this one is the cause and this one is the result. So that's why we know that B must be happen before C. Otherwise, C will not receive M. Okay. ចឹងក្នុងករណីមិញយើងនិយាយអំពីម៉ោងឬមួយក៏ event នៅពេលដែលកុំព្យូទ័រតែមួយទេតទៅឥឡូវយើងនិយាយកុំព្យូទ័រ2ម្ដងអញ្ចឹងបើកុំព្យូទ័រ2ហើយមានការផ្ញើសារទៅវិញទៅមកអញ្ចឹងអា event ដែលជាអ្នកផ្ញើ message ហ្នឹងវាច្បាស់ជាកើតឡើងមុនអា event ដែលជាអ្នកទទួល message ឯងតោះណា understand and there exists an event C such that A happen before C and C happen before B. So another problem, why do we know that A happen before B? Because there is a middle event. So that middle event is A is happen before C, and then C is happen before B. So as a result, A is happen before B. Okay, so that is also a happen before relationship between A and B. The happen before relationship is a partial order. It is possible that neither A happen before B or B happen before A. So in that case, we call A and B are concurrent, and the symbol of concurrent is two parallel lines. Okay. So if we don't know A happen before B or B happen before A, it means that those two events may happen at the same time or maybe happen in parallel. So in that case, we call that the two events are concurrent. So we don't know which one comes first. Okay. So in that case, we in the technical term we call it concurrent. អញ្ចឹងយល់កន្លែងហ្នឹងអត់ព្រោះអាហ្នឹងវាស្រៀងវារៀងលក្ខណៈ technical តិចវាម៉ាត់តិចបានន័យថាបើយើងចង់ដឹងថា event មួយណាកើតមុន event មួយណាកើតក្រោយទីមួយយើងពឹងទៅលើថាវា happen នៅក្នុង computer តែមួយឬមួយក៏ computer ច្រើនបើ computer តែមួយទេអាណាកើតមុនគឺវាដឹងតែមុនហើយតោះណាដល់ពេលតាក់ទងមួយ computer ច្រើនមានន័យថាម៉េចមានន័យថាអា send វាច្បាស់ជាមកមុនអា receive ហើយវាច្បាស់ជា send វាច្បាស់ជា happen មុនអា receive ដល់ពេលបើសិនជា event 2ហ្នឹងយើងអត់ដឹងទេបានន័យថានៅក្នុងកុំព្យូទ័រតែមួយក៏វាមិនមែនដែរវានៅក្នុងកុំព្យូទ័រច្រើនហើយក៏វាអត់មាន relationship ដែរយើងមិនដឹងថាមួយណាមកមុនមួយណាមកក្រោយទេអញ្ចឹងពេលហ្នឹងគឺយើងហៅវាថា2 event ហ្នឹងគឺវា concurrent ហើយ understand question so now we know that what is event. Okay, what is happen before relation. Okay, and then how do we know that two events are happen before or after or concurrent? Okay, so any question related to that, like what is an event, what is a happen before relationship, how do we know that two events happen before or after or concurrent? Understand? If understand, say yes. If not, you can ask the question. ចឹងយល់ហើយយល់មេរៀនឡើងហ្នឹងចំណុចកន្លែងហ្នឹងតិចទេបើយល់ចាំតែមកទៀតហើយបើយល់ដាក់ yes មួយម្នាក់មួយមក Hello អញ្ចឹង Understand? If
Hello,
understand,
teacher.
huh?
I have question.
Okay, you can ask.
Speak my teacher.
Nó là vậy mà.
Teacher, nó phải đài rồi. Cái công tơ môi sân mình sẽ nắng ảnh dân sân tới công tơ xây tiết đi cho.
Nó ngày sen tới công tập xây tiết.
Chẳng nó phải đài ảnh dân kịch môn cho nó phải
ảnh sen tới môn. Dươngអត់តន់និយាយរឿងអាពីរទៀតដែលអ្នកទទួលណាយើងនិយាយតែរវាងអាអ្នកសែនហើយនិងអាអ្នកទទួលមានន័យថាអាអ្នកសែនវាច្បាស់ជាមុនអាអ្នកទទួលហើយតោះណាតែយើងអត់ចង់និយាយអំពីអាអ្នកទទួល2នាក់នោះអាណាទទួលមុនអាណាទទួលក្រោយទេយើងតែនិយាយអំពីអា2នាក់ដែលអាមួយសែនអាមួយទទួលទេអញ្ចឹងអាសែនវាច្បាស់ជាមុនអាទទួលហើយយល់ហើយហ្នឹងនៅហ្នឹងហើយឧទាហរណ៍មិញហុកមិញវាមាន A B C អញ្ចឹងយើងអត់និយាយរឿង B C ទេយើងនិយាយរឿងតែ A ហើយនិង B ទេយើងនិយាយរឿង A B អញ្ចឹងបើ A វាអ្នកសែនអា B អ្នកទទួលច្បាស់ជា A មុនអា B ហើយតោះណាតទៅពេលអា B អា C បានយើងចាំគិតតទៀតអូខេOkay, so the question is, for example, like if the message is sent not locally but from computer 1 to computer 2 from computer C like this. So, for example, like in this case, we said that the event that send the message must be happen before the event that receive the message. Okay, but we don't talk about in this case, for example, like the same message sent to two computer and then which one do it arrive first? For example, like M1 arrive to B first or M1 arrive to C first. We don't talk about that. Okay, we only in this case we only talk about one computer. So now we know that one computer is A and B. So A must be happen before B. So if B and C, B must be happen before C. Okay. So if C and D, C must be happen before D. And if D and F, D must be happen before F. Why? Because if it is locally, we can count the time. But if it is transfer to a different machine, we count the sender must be happen before the receiver. Okay, we only talk about that. We don't talk about the multi communication yet. Okay. Okay, so let's see this example. So in this example, we have three computer. We have event A, B, C, D, E, F. So we want to know which event happened before which event and which event are concurrent. Okay. So if we count A and B, so A must be happen before B because it is happen at the same computer, and then A is happen before B. That in that case we write A arrow B. Okay. So A happen before B, C happen before D, E happen before F because the first one is those process are running in the same computer. And the other thing, B happened before C, so B happened before C, D happened before F. Why? Because it is the message sending, so the sender must be happen before the receiver. Okay. And the other one, for example, like A happened before C. Why do we know that A happened before C? Because there is a transitivity. Okay. So if A happened before B and B happened before C, we can say that A must be happen before C. Okay. ចឹងក្នុងករណីទី3មិញយើងនិយាយតែពីរករណីឯករណីទី1វានៅក្នុងកុំព្យូទ័រដូចគ្នាករណីទី2វាឆ្លងកុំព្យូទ័រចឹងអា send វាមុនអា receive ករណីទី3តាក់ទងជាមួយនឹងរឿង transitivity នេះមានន័យថាដោយសារតែ A កើតមុន B ហើយអា B នោះវាកើតមុន C ចឹងនាំឲ្យយើងអាច conclude បានថា A វាច្បាស់ជាកើតមុន C ហើយតោះណាចឹងso the third case is a transitivity. A happened before B, B happened before C. We know that A must be happen before C. So A happened before C, A happened before D, same thing. There is a two transitivity, so A must be happen before D, A must be happen before F, B must be happen before D, something like this. So those are the transitivity, okay? But the last one, for example, like A and E happen within different computer. And then there is no message sending, there is no execution locally. And then we don't really know, even if E is happen a little bit later before A, but we really don't know because the two computer has two different clocks, so we don't know which one is coming first. Even in reality, E is happen after A, but in the message ordering, we said that we don't know. Okay, so if there is no relation between them, we said that even A and even E is concurrent event. Okay, so we write this one. អញ្ចឹងមានន័យថាបើទោះបីជានេះយើងឃើញបើសិនយើងគូសម៉ោងទៅអា E នេះវាដើរយឺតជាងអា A នេះក៏ដោយក៏តែយើងអត់និយាយថា E ហ្នឹងវា happen ក្រោយ A ទេដោយសារអីដោយសារតែទី1វាអត់គោរពតាមអាច្បាប់3ខាងលើនេះទី1វាមិនមែននៅក្នុងកុំព្យូទ័រតែមួយអញ្ចឹងបើវាមិនមែននៅក្នុងកុំព្យូទ័រតែមួយយើងអត់ដឹងថាមួយណាមុនមួយណាក្រោយទេតោះណាទី2វាមិនមែនជាវាអត់មានបាន send message ឲ្យគ្នាទៅវិញទៅមកអញ្ចឹងយើងអត់ដឹងថាមួយណា sender អាមួយណា receiver ទេ ដល់ពេលទី3វាអត់មាន transitivity មានន័យថាវាអត់មាន event ណាដែលនៅចន្លោះកណ្ដាលអាពីរហ្នឹងដែលធ្វើឲ្យអាមួយយើងដឹងថាអាមួយកើតមុនអាមួយទៀតទេតោះណាអញ្ចឹង in that case យើងនិយាយថាអាពីរហ្នឹងវាកើតឡើង in parallel ឬមួយក៏ concurrent ហ្នឹងទៅបានថាយើងអត់ច្បាស់ទេបើទោះបីជាវាកើតឡើងក្រោយឬមួយក៏មុនតិចតួចក៏ដោយក៏តែយើងអត់ច្បាស់ហើយអាយើងអត់ច្បាស់ហ្នឹងហើយយើងហៅវាថា concurrent okay so you see that there is four case. So the first case we know that locally, the second case sending message, the third case is transitivity, and the last case if there is no three cases above, we say that it is concurrent. Okay, so E is concurrent with E, A is concurrent with E, B is also concurrent with E because we don't know B and E which one come first. Okay, so that is called happen before relation. So normally now we know that there are two types of clock. The first one we call it physical clock. So physical clock we are referring to the time, for example like the epoch time or the monotonic time. So those are the physical clock. But for writing a distributed system, sometimes we need another clock. We call it logical clock. Okay. So logical clock is not a clock. It's not a like a 1 minute, 10 minute clock like that. Logical clock is just a number to represent an event, which event happened before another event. Okay. So remember that in distributed system, we have another type of clock we call logical clock. It is not a physical clock. It is not atomic clock or epoch clock or monotonic clock. It is another type of clock, and those clock is normally just a number, or we call it an event. For example, like if one event happen another an event, we said it's just like one event is before another event. Like one event is happening at 1 o'clock, another event happening at 2 o'clock. Okay, but we don't say 1 o'clock, 2 o'clock. We say 1 and 2. So those number 1 and 2 we call it logical clock. Okay. អញ្ចឹងនៅក្នុង distributed system បើយើងនិយាយពីម៉ោងវិញវាមានម៉ោងមួយប្រភេទទៀតយើងហៅឲ្យឈ្មោះវាថា logical clock វាម៉ោងអញ្ចឹងវាមានពីរយើងដឹងហើយ physical ហើយ logical អា physical ហ្នឹងគឺយើងសំដៅទៅលើម៉ោងមែនតើបើថ្ងៃហ្នឹងម៉ោងប៉ុន្មានខែប៉ុន្មានអីចឹងទៅឬមួយក៏ម៉ោងកុំព្យូទ័រយើង start up ហ្នឹងក៏វាជាម៉ោងមែនតើដែរក៏តែនៅក្នុង distributed system យើងអត់អាចយកអាម៉ោងហ្នឹងជាគោលបានទេព្រោះដោយសារតែវាកុំព្យូទ័រហ្នឹងវាអាច slow អាចលឿនឯងយើងអត់ដឹងថាមួយណាមកមុនមួយណាមកក្រោយអញ្ចឹងគេបង្កើតម៉ោងមួយទៀតគេឲ្យឈ្មោះថា logical clock ដែល logical clock ហ្នឹងវាមិនមែនជាម៉ោងទេវាគ្រាន់តែជា number ឯងបានន័យថាវាជា event អញ្ចឹង event ណាមកមុន event ណាមកក្រោយអញ្ចឹងទៅវាដាក់លេខ1លេខ2លេខ3លេខ4អញ្ចឹងណាឲ្យថា event លេខ1 event លេខ2 event លេខ3អញ្ចឹងទៅអញ្ចឹងអាលេខហ្នឹងឯងយើងឲ្យឈ្មោះវាថា logical clock បងណា So the other thing is the term is called causality. So what is causality? If A happened before B, we might say that A might cause B. So A cause B to happen. Okay. If without A, there is no B. For example, like in this case, if B is not sending a message to C, there is no event C happen. Okay. So if there is an event like this, for example, like if B happen and before C and B sending some message to C, so we said that B cause C to happen. Okay. So that is called a causality. អញ្ចឹងមានន័យថាបើសិនជាយើងនិយាយអំពី event ណាបើន័យថា event C នេះវាកើតឡើងដោយសារតែ event B នេះវាកើតឡើងហើយបើអត់មាន B ក៏វាគ្មាន C កើតឡើងដែរតើណាអញ្ចឹងអាលក្ខណៈបែបហ្នឹងយើងហៅថា causality. So when B A and B is concurrent, we know that A cannot have cause B. So if there is a parallel event or concurrent event, for example like A and E like this, we don't know which one cause which one. Okay, so there is no causality. Happen before relationship and code potential causality. Physical clock useful but may not consistent with the causality, and logical clock designed to capture the causality dependency. So why distributed system design another clock called logical clock? Because logical clock can capture the causality. We know that B may happen before C may happen before D, something like that. But for example, like A and E, if we count on the physical clock, we don't know which one caused which one and which one happened before which one. Okay, so that's why distributed system need another clock called logical clock. And then we will see that the first type of logical clock is a Lamport clock algorithm. So normally Lamport is the one who study about distributed system, and then he create a lot of algorithm and write a lot of papers. So that's why his algorithm is very famous. Okay. But currently we don't use it anymore because it is long ago. But we just learn for the history, like how the logical clock happen. អញ្ចឹងត្រូវចាំថានៅក្នុង distributed system ម៉ោង physical clock มันអាចបញ្ជាក់ថា event មួយណា កើតមុនឬមួយក៏អីឬមួយក៏ cause event មួយទៀតឲ្យកើតឡើងបានទេដោយសារតែយើងដឹងថានៅពេលដែលម៉ោងនៅលើកុំព្យូទ័រពីរវាអាចខុសគ្នាវាអត់អាចដូចគ្នាបានទេអញ្ចឹងអា physical clock ហ្នឹងយើងអត់អាចយកវាជាការបានទេមូលហេតុហ្នឹងហើយបានគេបង្កើត clock មួយទៀតឲ្យឈ្មោះថា logical clock ហើយអា logical clock ទី1ដែលយើងត្រូវរៀននេះគេឲ្យឈ្មោះថា lampok clock អូខេអញ្ចឹងអា lampok clock ហ្នឹងគឺជា logical clock ហើយតោះណា So again why do we need logical clock because physical clock is not capturing a good causality between the event. That's why we create a logical clock. And then the first example of the logical clock is called Lamport clock. Okay, and another logical clock is called vector clock. So those are the logical clock. So now let's talk about Lamport clock algorithm. So Lamport clock algorithm is not 1 second, 2 seconds, something like that. As we know that the logical clock is just a number. So if an event happen, we call it 1. If an event 2 happen, we call it 2. And then if 2 send message to another computer, so we must add the number. For example, like here is a number 2. So if it sends something to here, this event must be 3, something like that. Okay. And then for example, like here is in the local computer, if this event is 2, this event must be 3. Okay. And then in another computer, so for example, like if this event is 3, another event must be 4 because we add 1. So whenever there is a new event, we just add 1. So that is called clock. Okay, increment just like a counter. And then if, for example, like if computer C, so if there is no event happen, we call it 1. But why we call this one 5? Because this event is the causality of this event 4. Okay, so 4 sending some message to computer C. So when the event here has a clock logical clock 4, it increment 1, it becomes 5. So 1, 2, 3, 3, 4, and 1, 5 are the logical clock. And the idea of counting this one, like for example, like if it is in the local computer, we increment it 1, 2, 3, 4, 5. If we send message from one computer to another computer, we use the clock from that computer plus 1. Okay, so that is we call it a Lamport clock algorithm. Understand? Understand how Lamport clock algorithm work ចឹងតនអត់បានន័យថាម៉ោង logical clock ហ្នឹងហើយឧទាហរណ៍ទី1គឺគេហៅ Lamport clock ហ្នឹងចឹង Lamport clock ហ្នឹងគឺជា logical clock ហើយចឹងឥឡូវយល់អត់ថា Lamport clock ហ្នឹងវាដំណើរការមិនបានន័យថាគេបង្កើតម៉ោងហ្នឹងដោយវិធីណា Understand? Hello? Yes, no? Okay. ពន្លឺយល់អត់ Okay. Yes 2 នាក់អ្នកផ្សេងទៀតយល់អត់ So now you know that there is a 2 type of clock in the distributed system. A physical clock we have learned, atomic clock, monotonic clock, something like that. Those clocks are very useful but cannot say which event happened before another event. So in distributed system we create another clock called logical clock. So logical clock is not a real clock like 1 minute, 2 minutes, 3 minutes, 1 hour like that. It is just a number, okay, an increment number. So when an event happen, we say it 1, another event happen, 1 plus 1, 2, another event happen, 3, something like that, 3, 4, 5, 6, 7, like that. So the first logical clock that we have learned is called Lamport clock. Lamport clock, when the clock is in one computer, when an event happen within a local computer, one computer, we just increment it 1, 2, 3, 4, 5, 6, 7 like this. But when an event cross from one computer to another computer, we just use the time in the local computer plus 1. Okay, so if this one is 2, this one must be 3. If this one is 4, this one must be 5. Okay, not 1, 2, not 1, 2, 3, 4, 5 like this. 1 is 5 because this event is the result of the other event that happening before it. So that's why the time here is 5. So if we want to compare like this event and this event, which one is happened before the other event? So 3 must be happened before 5. Okay. So but why we know that? Because 3 is less than 5. Depend on the Lamport clock. Okay. So if 3 is less than 5, so which means 3 is must be happened before 5. Why? Because 3 is happened before 4 and 4 is happened before 5. In transitivity, 3 must be happened before 5. Understand? So by using Lamport clock, we can ordering a message easily. Which message happened before another message? But if the time is the same, for example, like this is 3, this is 3. We don't know which one happened first. Okay. because when this one is sending this one and then this one is happening, so both event we don't know which event is happened before, so that's why there's the same clock, logical clock is 3 and 3. So we said that those events are concurrent. Okay, understand? So this is how Lampok solve the message ordering problem. តោះណាអញ្ចឹងបានន័យថាដើម្បីដឹងថាអា message ហ្នឹងអា message មួយណាមកមុន message មួយណាមកក្រោយគឺគេបង្កើត logical clock មួយដែលឲ្យឈ្មោះថា Lampok clock ហ្នឹងហើយតទៅអញ្ចឹងយើងឃើញហើយយើងអាលេខ1លេខ2លេខ3ហ្នឹងវាប្រៀបដូចជាម៉ោងអញ្ចឹងបើយើងនិយាយថាអា event មួយនេះវាកើតឡើងលេខ3ដូចម៉ោង3អញ្ចឹង event មួយនេះវាកើតឡើងលេខ5ដូចម៉ោង5អញ្ចឹងធម្មតាអញ្ចឹងអាម៉ោង3វាច្បាស់ជាកើតមុនម៉ោង5ហើយយោងទៅតាម Lampok algorithm ហ្នឹងហើយបើសិនជាយើងមិនមើលតាមអា Lampok ហ្នឹងក៏យើងដឹងដែរថាដោយសារតែអា3នេះវាកើតឡើងមុនអា4ហើយអា4នេះវាកើតឡើងមុនអា5អញ្ចឹងនាំឲ្យ3នេះវា 100% វាច្បាស់ជាកើតមុនអា5ហើយតោះនេះបើយើងបាច់មើលអាលេខ3លេខ5ហ្នឹងក៏យើងដឹងដែរដោយសារតែយើងសិក្សាមិញថា event 2នៅក្នុងមួយ computer បាទអាណាកើតឡើងមុនអាហ្នឹងវាមុនអញ្ចឹង3វាមុន4ហើយតោះដល់ពេលអា send message អា send វាច្បាស់ជាមុនអា receive ហើយតោះនេះអញ្ចឹងនាំឲ្យ3មុន4 4មុន5 3ច្បាស់ជាមុន5ហើយអូខេ understand? So Lampok algorithm is very long ago, and he is the initiator of creating a logical clock. But we don't use it anymore because it is very old. And then people start to think about another idea of creating a time. For example, like how do we make an accurate time when we have a lot of computer and when those computers sending message to each other. Okay. So the most basic one is Lampok clock. And this is a little bit advanced. So now we don't have one number. We have 3 numbers. For example, like so we call it vector. So if you know mathematics, vector is a combination of a lot of elements like this. So in Lampok clock, we only have only single clocks like 1, 2, 3, 4, 5 like this. But in a vector clock is a set of vector. So we have if we have 3 computers. Within one vector, we have three attributes. So the first one is belong to computer 1, the second one is belong to computer 2, and the third one is belong to computer 3. So here is just like a logical clock. So now if A has an event, and then this one we call event 1. So A here is 1, this one is 0, 0. Why is 0, 0? Because A haven't received event from B and C yet. Okay. Same thing is here. For example, like C has 1 event. So we know that there's no event from A yet, there's no event from B yet. So now there's 1 event from C itself. So we said that the time is 0, 0, 1. And then it is in the form of vector. Okay. So let's see again. So this one, event 2. So now this event 1 is event 2. So we can see that the clock, like Lampok clock, is incrementing 1 and 2. But still we don't have this 2 number because we don't receive anything. Okay. Now let's say this one send a message to here. Okay. So if this one send a message to here, if we talk about the time of the A is already 2. That's why here we see the number 2. Okay. But within the computer B, this is the first event of itself. So that's why the time is 1. Okay. So in this case, the logical time is written in the term of the vector, and then all the vector are the event of all the 3 computer or all the 3 nodes within the distributed system. អញ្ចឹងម៉ោងមួយទៀតគឺយើងនិយាយអំពីម៉ោងគេហៅ vector clock អញ្ចឹង vector clock ហ្នឹងគឺវាមិនមែនម៉ោងតែមួយទេអញ្ចឹង Lampok clock វាមានតែមួយតទៅពេលអា vector ហ្នឹងពាក្យថា vector គឺវាមានមួយ set ចេះអញ្ចឹងបើវាមាន3 computer អញ្ចឹងវាច្បាស់ជាមាន x y z ទេអូខេ x y z or you can talk call it abc. Okay. abc so abc is the name of the computer. Why we have this one? Okay, so for example, like if you have 5 computers, so your vector clock must be vector clock must be A, B, C, D, E. Okay, if you have 5 computers and those 5 computers need to talk each other, your vector clock must be have a lot of elements inside the vector. Okay, so A represent the clock in the vector A, B represent the clock in the computer B. So if it happen locally, those vector element must be increased, and if it's sent to the other vector, the number of the old computer need to send to the other computer, and then the counter is count from within the local computer. So you can see that this is the even 1 of computer B, and then this is the even 2 of computer B. So that's why you see that the time is 210, and then this is 220. So if we want to compare which clock happened before which clock, we compare all the vector. Okay, we use the vector to compare the clock. Understand? Yes, no, okay. Chẳng vô làm pi logical clock nữa. Logical clock គឺយើងlogical clock យើងមានពីរប្រភេទហ្នឹងថ្ងៃហ្នឹងយើងរៀនexample 1 is a Lamport clock, is also a logical clock, and vector clock is also a logical clock. Okay, and maybe there is another matrix clock or whatever. So those are the logical clock. តោះយល់អត់
អត់ទល់លោកគ្រូខ្ញុំសុំ get back to អា Lamport clock នេះបន្តិចបានទេលោកគ្រូកន្លែង concurrent របស់លេខ3លោកគ្រូ
ហ្នឹងហើយ
Lamport បាទចុងធម្មតានៅក្នុងកុំព្យូទ័រ A វា1វា happen before 2ហើយ2 happen before 3ប៉ុន្តែបើសិនជា2ពេលវា send message ទៅ B វា transition ពី2ទៅ3ប៉ុន្តែមិនបាន3របស់ A វា concurrent មួយ3របស់ B អញ្ចឹងលោកគ្រូ
ដោយសារតែ3ហ្នឹងបើសិនជាយើងមកមើលអាច្បាប់លើនេះអាច្បាប់4ដែលយើងរៀនពីមុនណានេះយើងមើលអា4ហ្នឹងសួរថាតើវាចូលទៅករណីអា3លើអត់ ឥឡូវយើងយកអាសំណួររបស់យើងហ្នឹងយើងយកមកមើលតើវាចូលទៅក្នុងករណី3លើអត់អូខេឥឡូវបញ្ចូលជាអង់គ្លេសមុនណា So the question is why 3 in computer A and 3 in computer B is concurrent. Why there is no like which one is happened before which one, something like that. So we need to see our case here. For example, we have 3 cases about. Okay, so the first case we use the first case. So the first case, does 3 and 3 here happen in the same computer. ចឹងសំណួរទី1សួរថាតើអា2 event ហ្នឹងវាកើតឡើងនៅក្នុងកុំព្យូទ័រតែមួយអត់ Yes or no?
No.
Yes or no?
No.
Okay, so no, which means the first case is not correct. Okay, so the first case is not correct. So which means we don't know. The answer is we don't know. We don't know if this 3 happened before this 3 or this 3 happened before this 3 because it is not happened before. It is not happened in the same computer. Okay, so that is the case 1. So case number 2. Case number 2, does this 3 send message to this 3 or this 3 send message to this 3. ចឹងសំណួរទី2សួរថាតើអា event 2ហ្នឹងវាមាន send message ឲ្យគ្នាទៅវិញទៅមកអត់
No.
Yeah, no. So that means case 2ក៏វា incorrect ដែរតោះណាហើយធម្មតាតែ case វា incorrect មានន័យថាយើងអត់ដឹងទេយើងអត់ច្បាស់ថាមួយណាមុនមួយណាក្រោយទេ Okay, so now 2 case is incorrect, which means we don't know. Okay, we don't know this 3 is happened before this 3 or this 3 happened before this 3 because it is not happen at the same computer. It is not send message to one another. So the third case, is there any transitivity between the two event? For example, like 2 happened before 3, 3 happened before B, before 3, then this 3 must be happened before 3, something like that. Is there any transitivity event? ចឹងយើងអាទី3ហ្នឹងយើងគិតតិចថាតើមាន event ណាដែលវានៅចន្លោះកណ្ដាលអា2ហ្នឹងឯងដែលយើងអាចនិយាយបានថាដោយសារតែអានេះវាកើតមុនអាមួយនេះកើតមុនអាមួយនេះចឹងនាំមកអាមួយនេះកើតមុនអាមួយនេះឬមួយក៏អាមួយនេះកើតមុនអាមួយនេះអាមួយនេះកើតមុនអាមួយនេះនាំមកអាមួយនេះវាកើតមុនអាមួយនេះហ្នឹងទៅសួរថាវាមានអា transitivity event ហ្នឹងអត់
ខ្ញុំយល់ទេលោកគ្រូហ្នឹងហើយយល់ដោយសារខ្ញុំគិតថាដោយសារតែអា2នោះវាសិនទៅ3ហើយអា3នោះវាកើតក្រោយអា2នេះហ្នឹងហើយអា3នេះវាកើតក្រោយអា2នេះទេអញ្ចឹងបានន័យថាវាមិនមែនអានេះទៅ3ហើយតោះតែអាមួយនេះវា send មកវិញបានអានេះចេញ4តោះណាតែដោយសារតែវាអត់ send មកវិញទេហើយវានៅកន្លែងហ្នឹងទេអញ្ចឹងវា3តោះពេលអញ្ចឹងដូចខ្ញុំនិយាយមកអញ្ចឹងអានេះយើងហៅ logical clock តែបើសិនយើងមើល physical clock វិញខ្ញុំឧទាហរណ៍ថាអា2នេះ send អានេះវិនាទីទី2ចុះវា send មកដល់នេះ3វិនាទីអានេះវិនាទីទី3តោះពេលអានេះមកកើតឡើងវិនាទីទី4ចុះឧទាហរណ៍ថាអញ្ចឹងចុះអញ្ចឹងបើទោះបីជាអានេះ4អានេះ3ក៏ដោយអាហ្នឹងវាជា physical clock ទេតែក្នុងករណីនេះគឺយើងនិយាយរឿង logical clock យើងអត់និយាយរឿង physical clock យើងបានន័យថាអា2ហ្នឹងយើងមិនច្បាស់ថាអាមួយណាកើតមុនអាមួយណាទេដោយសារតែវាអត់មានអា3 relationship 3 case ខាងលើអញ្ចឹងទោះបីជាអាមួយនេះវាពិតជាកើតមុនអាមួយនេះមែនឬមួយក៏អាមួយនេះវាពិតជាកើតមុនអាមួយនេះមែនដោយសារតែវានៅក្នុងកុំព្យូទ័រផ្សេងគ្នាយើងសន្មតថាយើងអត់ដឹងហើយអាយើងអត់ដឹងហ្នឹងហើយយើងហៅវា concurrent. Okay, យល់លោកគ្រូ
Okay, so in logical clock we are not talking about physical clock. Even if this event happened before this event or this event happened before this event, we said that we don't know because we are not talking about the real physical time. We are talking about which event happen before another event, which so we have a happen before relationship, which if event cause another event, something like that. So if these two event, there is no three case above, like this three case, there is no case like the event. There's no the event, two event is not happen within the same computer. There is no sending receiving message. There is no transitivity even happen in the middle. We said that we don't know, and then these two events are concurrent according to the logical clock or Lamport clock. Okay, so that's why we see that this clock is number 3 and this clock is number 3. So Lamport clock is only count one number. So you can see that all the 3 computer has only one single clock, like 1, 2, 3, 4, 5, 6, 7, like this. So we can say that this event number 1 is happen before the event number 5 because 1 is less than 5. Okay, so this event number 3 is for example like happen for example like happen what happen after this one, because this one is 1, something like that. Okay, but in the vector clock, if we have a lot of computer, the number of the clock is in the form of the vector, and those elements are the number of the computer. If we have 3 computer, we have 3 elements in the vector. If we have 5 computer, we have 5 elements in the vector. And then the row, the number of column is the position of the computer itself. So if computer A has one event 1, 2, 3, you can see that 1, 2, 3 is here. And then when it's sent to something else, it also send it local clock. And then the other computer may increment their local clock also. Okay, so 2 and 1. Okay, so these are the example of a logical clock. And then now, if you see the modern distributed system, for example, like in this case, I don't really go deep down to this system, but I only want to show you like how they solve the messaging ordering problem or the clock problem in the distributed system. Okay, so for example, in this case, we have a lot of computer. Not so here you can see only there are only 3 computer, but in this case there are a lot of computer, like 1, 2, 3, 4, 5, 6, 7, 8 computer. Okay, so 8 people using different 8 mobile phone or 8 machine, or maybe within the real distributed system there is 1 million users. So we can see that those are a lot of computer. And then when those people communicate with each other within the system, like this one send mess in, for example, like we can use one example like sending money. Okay, so if this one sending money to this one sending money to this one sending money to this one, this user sending money to this user, something like that, we would like to know which transaction happened before another transaction. Okay, so in this case we cannot use a single clock or a physical clock, because those clock are happening within the different computer. So that's why we need to have a relationship between an event. So each event happen in the computer, we call it event. And then there's also a relationship between one event to another event. Okay, so you can see that there's a relationship between an event and event. And then after that, you in this we call a hash graph gossip protocol, you can see that they also define the color of the event. For example, like this color is red, this color is white, this color is green, something like that. For example, like those event also has their own state. For example, like if the event is happened very long time ago, we say that okay, this event is already done. We just like a database, we commit the data, something like that. But if the event is just happening, we don't know which one come first, which one come last. It is in another state, like a blue state or a green state, something like that. So those type of data is just like a pending data. Okay. But we will talk more when we learn about blockchain technology, because a hash graph is one kind of blockchain. Okay, but in this diagram, I just would like to show you how the logical clock work. Okay, if we don't have a real computer clock, people need to find the solution to create a clock. So the logical clock, it just look like a graph. So we call it a graph. So a graph, there is a node, and then there is an edge, and then they talk to each other, something like that. Okay, and then you can see that there is a different kind of color which represent different kind of state. So some state is already a good state, a very strong state, and some state are very new, very fragile, and easy to confuse. Okay, so normally when we want to agree on something, we need to agree on something which is already strong or rigid, something like that. But we don't agree on something that is confusing or still talking to each other. Okay, so that is the idea of the clock in the distributed system. អញ្ចឹងនៅក្នុង distributed system ខ្ញុំបញ្យល់ជាខ្មែរមួយផ្លែទៅ ដោយសារតែ computer វាមានច្រើនហើយយើងដឹងថាម៉ោង computer វាអត់ដូចគ្នាទេវាខុសគ្នាតិចតួចដោយសារតែវាមាន error ស្អី quad ស្អីអស់ហ្នឹងអញ្ចឹងគឺគេបង្កើត logical clock ហ្នឹងអញ្ចឹងពេលដែលមានឧទាហរណ៍ក្នុងករណីនេះដូចមនុស្សផ្ញើលុយឲ្យគ្នាទៅវិញទៅមកអញ្ចឹងមនុស្សនេះផ្ញើលុយឲ្យមនុស្សនេះផ្ញើលុយឲ្យមនុស្សនេះតទៅពេលហើយគេចង់ដឹងថាតើក្នុងចំណោមលុយទាំងអស់ហ្នឹងtransaction លុយមួយណាវាកើតមុនលុយមួយណាតោះណាអញ្ចឹងដើម្បី solve problem មួយហ្នឹងបានគឺគេបង្កើតជា logical clock ហ្នឹងដូចយើងឃើញlamp clock Victor clock អីហ្នឹងតទៅពេលហើយគេបង្កើតឡើងអញ្ចឹងវានិយាយគ្នាចុះឡើងទៅវាមានrelationship របស់វាយើងដឹងថា event ណាកើតមុន event ណាអញ្ចឹងទៅតទៅពេលក្នុង modern system ឥឡូវហ្នឹងវាមានវា time state មួយទៀតមានន័យថា event ហ្នឹងទោះបីជាវាកើតមុនកើតអីមែនក៏តែគេដោយសារតែ event នេះវាកើតយូរហើយឧទាហរណ៍វាកើតតាំងពីថ្ងៃមុនមួយអាទិត្យមុនមួយឆ្នាំមុនហ្នឹងទៅអញ្ចឹងយើងជឿជាក់ថាវាពិតប្រាកដហើយតោះនេះវាច្បាស់លាស់ហើយអញ្ចឹងអាហ្នឹងគេហៅដូចថា event ហ្នឹងវាយូរវា strong វាអីចឹងណាតទៅពេល event ខ្លះមនុស្សតែមិនមកមិញទេតទៅពេលអញ្ចឹងevent ហ្នឹងគឺយើងអត់ទាន់ច្បាស់លាស់ហើយតោះណាអញ្ចឹងគឺគេបានបង្កើតជា state មួយមានន័យថាបើសិនជាវា happen យូរហើយយើងចាត់ទុកថាហ្នឹងវាច្បាស់លាស់ហើយគឺมันអាចកែប្រែបានទេក៏តែបើសិនជាវាទាំងផ្ញើមកថ្មីចេះវាអាចជួនកាលវាបាត់ចឹងទៅជួនកាលកុំព្យូទ័រហ្នឹងវានិយាយគ្នាអត់ទាន់ត្រូវគ្នាទៅអញ្ចឹង event ទាំងអស់ហ្នឹងបើទោះបីជាវាកើតឡើងមែនក៏យើងអត់ប្រកាសអត់ទាន់ commit វាចូលទៅក្នុង data មែនតើដែរអញ្ចឹង database យើងគឺគេបង្កើតមកវាមានគេហៅ commit state ហើយ pending state commit state មានន័យថាអូខេឥឡូវនិយាយគ្នាសម្រាប់យកអញ្ចឹងហើយឈប់កែហើយក៏តែតទៅពេល pending state មានន័យថាម៉េចវានៅមានការប្រែប្រួលតិចតួចនៅពេលដែល 3-4 ម៉ោងក្រោយឬមួយក៏ប្រហែលនាទីក្រោយមកបានpending state ហ្នឹងវាទៅជា commit state យល់ទេយល់ idea ហ្នឹងទេ understand so in the distributed system the clock is not very for example like exact like one point this one happened before this one not like that okay there's a little bit delay so it depends on which system you are using some system is delay 10 seconds some system delay 6 hours some system delay 1 second something like that so those kind of delay create different kind of state in the machine so that's why sometimes you learn there's something called a state machine okay so for example like this one is a state machine so there's a red state blue state green state so the red state is already committed to the system the green state or the blue state is still a pending state so waiting for another communication another commitment in order for the blue state to transit to the green state to the red state something like that okay យល់រឿងម៉ោងម៉ោងតាក់ទងមួយ distributed system មួយ distributed system វាមិនមែនកុំព្យូទ័រតែមួយគ្រឿងទេ1000គ្រឿង10000គ្រឿង1លានគ្រឿងអញ្ចឹងដើម្បីសិក្សាពីម៉ោងវាគឺយើងអត់យកអា physical ម៉ោងយកមកនិយាយគឺយើងយក logical clock មកនិយាយវិញអូខេហើយបើកុំព្យូទ័រនឹងតូចទេអា clock ហ្នឹងវាស្រួលទេ3 4គ្រឿងអីយើងដាក់តែ lamp clock ឬមួយក៏ Victor clock ទៅដើរហើយកុំតែបើកុំព្យូទ័រនឹងរាប់ពាន់គ្រឿងពេលហ្នឹងគឺយើងអត់ប្រើអញ្ចឹងទេតោះណាគឺគេមាន protocol ផ្សេងច្រើនទៀតដែលអាហ្នឹងយើងនឹងអាចរៀននៅពេលយើងរៀនមេរៀន blockchain អូខេហើយអា hash graph មិនហ្នឹងគឺជា blockchain មួយហើយ question any question so our clock lesson is finished now if we don't have question we can move on to the next chapter any point that is not clear so in the real system we may have two representation of clock or timestamp one might be a physical one like today is 2022 March 15 2 o'clock something like that but there is also something that represent which event happened before another event so those are the logical clock okay so when we want to compare two transactions which one happened before another one we can count on the logical clock and physical clock also okay and remember that in the distributed system there is no the decision is not made exactly within one point within instant of time there must be a little bit delay okay for example like I say that event A happened before event B but this event is only pending okay pending so for example like 10 seconds later when I learn some information from another computer those computers said that B is happened before A and then we all agree that B is happened before A so in the commitment state B is happened before A it just like that okay so example A we know that A happened before B so this is just in the distributed system it's just a pending event okay it's just pending because we only learn this information from one computer but distributed system there's a lot of computer for example like 10 computers said that B is happened before A okay and then there is a 3 computers said that A is happened before B so which one do you choose so there is we have 13 computer and 10 computers said that A happened before B B happened before A, and 3 computers say A is happened before B. So what are our conclusion? So number 1, A is happened before B, and then number 2 is B is happened before A. So which one do you choose? Đó, lấy ưu tiên hôm ưu tiên tha lấy dương miền bình đọc computer. Đọc computer nó viên vậy tha Bកើតមុន A តោះណាតទៅពេល3 computer ទៀតវានិយាយថា A កើតមុន B ឥឡូវសួរថាតើចង់បញ្ចប់យើងគួរយកចម្លើយមួយណាតើ A កើតមុន B ឬមួយក៏ B កើតមុន A ចឹងមានអ្នកឆ្លើយថាទី2ត្រូវហើយបានន័យថា B កើតមុន A ហេតុអីបានយើងយក B កើតមុន A ដោយសារតែមានមនុស្ស10អ្នកមើលឃើញអានឹងប្រៀបដូចជា witness ចឹងណា so those 10 we can call it a witness, okay, or an honest people, okay. Those 3 it might be honest or it might be malicious, okay, or it might be something faulty, okay. So that's why we normally count on something called majority. So we don't know if it is correct or not, but majority 10 computers said that B coming before A. These are only 3 computers, so we count on the majority. So as a result, we said that B is happened before A. Okay. So if I am the one between the 3 computer, I know that first in my database is A happened before B is a pending. Okay. But when I receive 10 more messages from the other computer, now I commit my database. So my database now is B happened before A, and no one can change it from now on. So from now on, B must be happen before A, and then this is a commit state. Okay, that is called a state. Understand? So you can see that we have a pending state, and then we have a commit state. Okay. In the future, there's a lot of state. It depends on how you design your system. Like my system has 2 states, my system has 3 states, something like that. Okay. So in the distributed system, everything is not making decision immediately. You need to wait for the other people to talk to you, and finally you make a decision. Okay. ចឹងនៅក្នុង distributed system យើងអត់មាន make decision ភ្លាមៗទេមានន័យថាទោះបីជា event ហ្នឹងកើតឡើងក៏ដោយក៏យើងមិនទាន់និយាយថាវាអញ្ចឹងដែរតើតែយើងដឹងពីព័ត៌មានពីច្រើនគ្នាមកទៅដូចយើងស្ដាប់ព័ត៌មាននៅលើ Facebook អញ្ចឹងណាបើមានគេផ្សាយមួយទៅយើងអត់ទាន់ជឿយើងទៅមើល 4 5 6 7 នាក់ទៅបើគេនិយាយអញ្ចឹងដែរអូខេទោះបីជាព័ត៌មានហ្នឹងខុសក៏ដោយក៏យើងជឿដែរដោយសារវាមានមនុស្សភាគច្រើនវានិយាយអញ្ចឹងណាអញ្ចឹងនាំឲ្យ majority យើងជឿវាអញ្ចឹងតទៅអញ្ចឹងទៅយើងមនុស្សយើងខ្លួនឯងមិនបាញ់យើងជឿលើព័ត៌មានទី1ដោយសារតែ10នាក់ទៀតគេមិនមែននិយាយអញ្ចឹងយើងជឿលើព័ត៌មានទី2អញ្ចឹងព័ត៌មានទី1ហ្នឹងប្រៀបដូចជា pending ព័ត៌មានអញ្ចឹងព័ត៌មានដែលយើងស្ដាប់ហើយតែយើងអត់ទាន់ជឿទេតទៅពេលព័ត៌មានទី2ហ្នឹងគឺយើងស្ដាប់ហើយយើងជឿហើយយើងសម្រេចយកអាហ្នឹងបានចាប់ពីថ្ងៃហ្នឹងទៅគឺយើងយកព័ត៌មានទី2ជាគោលអូខេ so let's talk about our third chapter, and it is also depend on it is continue from the chapter 3. It is related to the fault tolerance. Okay. So chapter 4 is a fault tolerance, and then we will talk about the definition of some fault. We have 2 problems to learn today. One is called 2 general problems. So there's only 2 computers, and the other one is a Byzantine general problem, which means we have more than 2 computers, like 3, 4, 5, and 2 until 1,001 billion computer. Okay. So there are a little bit definition that we must learn. So the first one, what is fault? You can see that here is fault tolerance. So what is fault? Fault is the cause of malfunction or error in the system. So whatever cause something to error in the system, we call it fault. Okay. So what is the difference between fault and failure? So failure is the effect. So normally it is just like a cause and effect. So this one caused something, and then when the effect happened, we call it the system now is failure, system failure. Okay. So remember the word fault is the cause, failure is the effect. So it is the effect due to the fault or the problem, either by the hardware or by the operating system, by the software, or by, that cause the system to end abnormally. Okay. For example, like when you run your computer and there is some error and your computer stop immediately. So the cause is called a fault, but when your computer is stop working, we call it failure. ច្បាស់នៅច្បាស់អាពីរហ្នឹងនៅ fault ហើយនិង failure ចឹង fault បានន័យថាគឺជាដើមហេតុហេតុណាដែលនាំឲ្យកុំព្យូទ័រយើងវាអត់ដើរអីណាហេតុហ្នឹងយើងហៅវាថា fault តោះណាតែតទៅពេល failure មានន័យថាវាជាផលវិញមានន័យថាអាកុំព្យូទ័រហ្នឹងវាលែងដើរឲ្យវាគាំងហើយចឹងវាគាំងដោយសារអីដោយសារតែដាច់ខ្សែភ្លើងចឹងទៅចឹងអាដាច់ខ្សែភ្លើងគឺជា cause តទៅពេលអាលែងដើរគឺជា failure ឲ្យច្បាស់អាពាក្យហ្នឹង fault and failure. And then the other one is fail safe. What is fail safe mean? Fail safe mean even if there is a fall happening, we want our system to fail safely, which means there is no crash on the system or the application is not stopped immediately. We just show some message to the user, something like that. Okay, now my system is on maintenance, something like that. So that kind of information, we call it a fail safe. Okay. So normally when we design a distributed system, we need our system to, if it fail, it must be fail safe. Okay. So in an event of the failure, the system chooses to fail in the manageable manner. So the system will not crash. That's why in the programming, you can see there's a lot of try and catch. So try if there's some error happen. Catch is the solution. Okay, you need to provide some kind of solution, like writing a message, something like that, or suspend your service, something like that, but not crash your application. Okay, so that is called fail safe. ចឹងច្បាស់ណាច្បាស់3ពាក្យហ្នឹងណា fall គឺជាដើមហេតុដែលនាំឲ្យមានបញ្ហា failure គឺជាផលដែលថាបញ្ហានោះកើតឡើងហើយវា result in system down ឬមួយអីហ្នឹងទៅអាហ្នឹងគឺ failure តទៅពេល fail safe មានន័យថាម៉េចវា fail មែនបើទោះបីជាវា fail មែនក៏តែយើងអត់ចង់ឲ្យវា fail អាក្រក់មើលពេកទេតោះណា fail ឲ្យវាល្អមើលអាហ្នឹងគេហៅ fail safe. And then fail safe is similar to fault tolerant. Okay, what does a fault tolerant mean? Which means that our system can deal with the fault. No matter how fault our system is or failure our system is, it can tolerate. Tolerate means it is still running. Okay, so we need something that even if it is failed, but our system is continue to run. So that is called a fault tolerant. Okay, so what are the type of the fault? So what can cause the problem? For example, like I don't have memory, no more memory in the system. Okay, memory overflow. CPU consumption, now there's a lot of application and then it costs 100% CPU consumption, something like that. So that are the fault. Okay, sometimes the cable is disconnect, so that are also the type of the fault. Okay, network timeout, you send something to the other computer and the other computer is not responding. Okay, so that are the some fault. Hardware failure, for example, like the hard disk burn or something like that. Okay, software error or bug, sometimes it is depend on human. You write some code, that code produce an error which cause your system to fail. Okay, so that is also a type of fault. So we are having a lot of falling type. Okay, it depends on hardware, software, network, or whatever, memory, CPU, something like that. So what are the solution? The only solution is to replicate. Okay, to backup, we call it replication, backup, redundancy. So the only solution, the most effective solution to those problems is replication. If you have one server, if your computer is down, it's down. Okay, but if you have two computers, one down, another one is still running. Okay, so that's why the idea of replication and redundancy is very useful in order to deal with the fault, and then we call it fault tolerant. ច្បាស់ហ៎ ចឹងបានន័យថាបញ្ហាវាអាចកើតឡើងដោយច្រើនរបៀបតាមរយៈ hardware software CPU memory ហ្នឹងទៅក៏តែតទៅពេលដើម្បីដោះស្រាយបញ្ហាទាំងអស់ហ្នឹងបានគឺធ្វើវាឲ្យមានច្រើនតនេះពី2ឡើងទៅ replication ហ្នឹង replication ហ្នឹងមានន័យថាបើសិនយើងមានស្អីក៏ដោយឲ្យតែយើងមាន2បើមួយអត់កើតអាមួយទៀតកើតហើយតនេះ server មួយ down សល់មួយ backup មកវិញទៅបង្កើតថែមមួយទៀតមកបាន2វិញដដែលចឹងទៅ Okay, so the second step, so now you know the definition. Now we learn about one problem when two computers is talking to each other. Okay, so we talk about two general problems. So why in the computer science we call two general problem? Because we are using the case in Byzantine Empire. So general mean the one who control a lot of army. Okay, so we have two general, which mean we have two army. And then these two armies want to attack a city, and those city is called the Byzantine Empire. Okay, so when we have two armies want to attack the city, how do the two armies agree with each other? Okay, so that is called two general problem. And we will see that if the two armies join force together to attack the city, it will win. But if only one go and one retreat, those the city will destroy the army because the city is very big. There's a lot of army. Okay, so in order to destroy the Byzantine city, we need two army go at the same time. Okay, but the problem is they cannot talk to each other because of one army is in another mountain, another army is in another mountain, and in order to talk with each other, they need to send someone go to the mountain, pass through the Byzantine city, and then go to another mountain in order to send the message to another general. Okay, that's why we call it two general problem. okay ចឹងតាក់ទងជាមួយនឹងរឿង two general problem ហ្នឹងគេឧទាហរណ៍ការសម័យ Byzantine Empire Byzantine ហ្នឹងគឺជានគរមួយដូចជាខ្មែរ Empire អញ្ចឹងណាហើយមានតបពីរហ្នឹងវាចង់មកវាយអាប្រទេសមួយហ្នឹងបើសិនជាតបពីរហ្នឹងរួមដៃគ្នាវាយបានឈ្នះតើណាតែបើមានតែតបមួយវាយតបមួយទៀតរត់ទេគឺអាពីរអ្នកហ្នឹងវាយអត់ឈ្នះអាតប Byzantine Empire ហ្នឹងឯងអញ្ចឹងអាពីរអ្នកហ្នឹងវាត្រូវនិយាយគ្នាថាតោះចូលវាយជាមួយគ្នាអញ្ចឹងពេលវាវាយជាមួយគ្នាបានវាឈ្នះបើវាអត់និយាយគ្នាត្រូវទេគឺវាវាយអត់ឈ្នះទេតើណាតែដើម្បីវាយបានវាអត់មាន telephone អីមកឬមួយក៏ internet Facebook អីឆាតគ្នាទៅវិញទៅមកថាតោះវាយទេតើណាវាត្រូវបញ្ជូនអ្នកនាំសារហ្នឹងត្រូវយកសបុតពីកន្លែងមួយឆ្លងកាត់ភ្នំមួយចុះទៅប្រទេសហ្នឹងហើយឡើងទៅប្រទេសនេះមួយទៀតឡើងទៅភ្នំមួយទៀតបានអ្នកនេះឃើញហើយតទៅពេលអ្នកនេះឃើញសបុតហ្នឹងបានយកឲ្យអ្នកមួយទៀតហើយបានមកដល់មេតបនេះវិញបានដឹងថាអូខេឥឡូវពីរអ្នកហ្នឹងត្រូវវាយមកប្រហែលបានចូលវាយមួយគ្នាយល់ use case ហ្នឹងហ៎ so remember two general problem is the problem between two general and two army who want to attack a city. If they both attack the city at the same time, they win. Otherwise, they lost. Okay. But in order to attack at the same time, they need to agree with each other by sending the message. And the message could go through the city and then go back, something like that, just like a network communication. Okay. And then those messages could be lost. So now let's see the first case. If the message loss happen, for example, like the first general sending the message to another general through the city. So it send and then it arrive. I want to attack. Okay. So now the first general lead the attack by sending a message. I want to attack. And then the second general sending a message. Okay, I attack too. Okay. So now the confirmation is clear from the second general that said that now I attack too. Okay. But when this general send the last message for commitment, like okay, now we all attack. This message is captured by the Byzantine city and then kill the messenger. Okay, so now this message is not arrived. So if this message is not arrived, can both general go to fight? Anyone can answer. Like general 1 go to fight alone, or general 2 go to fight alone, or both general 2 go to fight together. Which case? Which case? Okay, who can tell? So now this general send message to this general said that I will fight. Okay. Okay, so now I will fight. Okay. Or maybe we can say it attack. Okay, attack. I will attack. Okay. So this general send back the message. Okay, I will attack. Okay. But when this general sending the message, it crashed. Okay. For example, like one messenger passing through the city, and then they kill him. Okay. So now the last message is not arrived. So now the question is, which army go to fight to the city? The first answer is A, go to fight. The second answer is B. And then the third answer is A and B go to fight together. So which are the correct answer? តោះឆ្លើយសំណួរហ្នឹងចេញអត់មានន័យថាវាមានអាមេតប2ហ្នឹងវានិយាយគ្នាថាទៅវាយប្រទេសមួយហ្នឹងអាមេតបទី1នេះវាថាតោះទៅវាយតទៅពេលអាមេតបទី2នេះវាថាអូខេខ្ញុំទៅវាយអញ្ចឹងតែតទៅពេលអាមួយនេះវាថាអូខេដែរខ្ញុំទៅវាយដែរក៏តែអាពេលអូខេ message ហ្នឹងវាអត់បានមកដល់ដោយសារគេចាប់អាមួយហ្នឹងហើយគេសម្លាប់ចោលបាត់ហើយអញ្ចឹង message ទី3ហ្នឹងវាអត់បានមកដល់ទេតោះណាអញ្ចឹងសំណួរសួរថាតើអាមួយណាត្រឹមត្រូវអាមេតប A ចូលទៅវាយម្នាក់ឯងមេតប B ចូលទៅវាយម្នាក់ឯងឬមួយក៏មេតប2នាក់ហ្នឹងចូលទៅវាយទាំងគ្នាចូលទៅវាយទាំងអស់គ្នាគ្រាន់អាចខុសម៉ោងគ្នាលោកគ្រូតោះអ្នកផ្សេង So one student said that A and B go to fight together. Okay. How about the other person, the other student? អ្នកផ្សេងទៀតគិតមិនអា A ចូលទៅវាយម្នាក់ឯងអា B ចូលទៅវាយឬមួយក៏អា2ហ្នឹងចូលទៅវាយទាំងអស់គ្នា
I think only B who go to fight alone.
So B go to fight alone. Okay. So how about the other? ចឹងឥឡូវមាន2ចម្លើយ How about the other student? Anyone would like to say A? So some say A and B, some say B. What about the other? So that is why we call it what? We call it two general problem. Okay. because it is a problem. Even you, like how many of you now today? So now we have 66 students. Okay, so we have 66 students, and then some students say A and B go, some students say B go. So now if you are the general, okay, so if you are the general, some may go together, some may go alone, something like that. So that means the decision is not clear. Okay, so for example, like if we ask 1 + 1 is equal to what, everyone must say 2. Okay, but now when we ask if A go alone, if B go alone, if A and B go alone, we are not clear. Some say 2, some say 3, some say 4, some say 1, something like that. Okay, so when we are not clear like this, we said that this is a problem that we need to solve. Okay, that's why we call it two general problem. So now what are the real answer? មានណាគេច្បាស់អត់ថា answer ពិតប្រាកដមួយណា For example, like we can talk case by case. Okay, let's talk A. A want to attack because A is sending a message to B. Okay, and now B is giving the answer. Okay, I will go too. So if you are the general B, what will you do? Attack or not? We are not talking about B. We are talking only about A. If you are general A, do you attack or not?
Attack.
Yes. Okay, so attack. So A will go to attack because why? A want to attack, and then B also confirm that I want to attack too. Okay, so that's why A will go to attack the city. Okay, but do B go to attack or not? For example, like you see here, A want to attack. Okay, B said, okay, I attack too, but I wait for you to confirm me. Okay, and then A did not confirm. What will happen? Does B go to attack or not? B ទៅអត់ B ទៅអត់ ឧទាហរណ៍ថាឥឡូវចាត់ទុកថាយើងដូចពួកម៉ាក់2នាក់អញ្ចឹងណាយើងចង់អាមួយនោះវាធ្វើបាប A ទៅហើយយើងចង់ទៅវាយវាទៅឧទាហរណ៍អញ្ចឹងចុះឧទាហរណ៍នេះយើងកាចតិចតទៅពេលហើយណា A នេះប្រាប់ថាអូខេអាមួយនោះមិញវាយអញហើយជួយទៅវាយវា2នាក់តោះអញ្ចឹងណាបានន័យថាវាយ2នាក់មិនឈ្នះវាអាមួយនោះវាធំអញ្ចឹងទៅតទៅពេលអា A នោះវាប្រាប់អា B ហ្នឹងអា B ហ្នឹងតែវាមិនមែនបានន័យថាជួបមុខគ្នានិយាយគ្នាណាវាផ្ញើសារតាមសបុតតាមព្រៀបនាំសារអញ្ចឹងទៅផ្ញើមកបើ B អញ្ចឹងទៅប្រាប់ថាជួយទៅវាយអញទេអាមួយនោះវាធំវាវាយអញមិញតទៅពេលអា B ថាឥឡូវអូខេអញទៅវាយដែរកុំតែតរហែងប្រាប់អញផងថាហែងនឹងទៅវាយប្រកាសថានឹងទៅវាយតោះណាតទៅពេលអញ្ចឹងអា A នេះវាទទួលបានសបុតហ្នឹងហើយថាអញទៅវាយដែរតើឯងប្រកាសប្រាប់ថាឯងនឹងទៅវាយដែរអូខេតទៅពេលអា message ផ្ញើមួយនេះមកអាមួយនេះវាឃើញវាបាញ់ព្រៀបនឹងស៊ីបាត់តោះណាអា message ចុងក្រោយនេះវាអត់បានមកដល់ B ទេតទៅពេលអា B ហ្នឹងវាថាអញនឹងទៅវាយដែរកុំតែ complete confirm ប្រាប់អញផងថាឯងប្រកាសជាទៅតែអា message ហ្នឹងវាអត់បានមកដល់ទេអញ្ចឹងឥឡូវសួរថា B វាគិតមិនដែរ B វាសម្រេចចិត្តមិន
វាដេកទាំងគ្រូ
ហ្នឹងហើយវាដេកទាំងដោយសារអីវារងចាំថាអញចង់ជួយឯងដែរតែអត់លឺឯងថាចង់ទៅវាយហ្នឹងក្រៃលោឯងទុនចិត្តឈប់ទៅវាយវាវិញអញ្ចឹងណាតោះណា understand so A want to attack A receive a confirmation from B that want to attack too so A clear that B want to attack okay and A is clear that he sent back the message to B so tomorrow A will go to attack but B he said that I will help you to attack too but unless you confirm me that you really want to attack something like that okay but we waiting for those message and didn't come so that's why we still waiting for the confirmation and then tomorrow happen B didn't receive the message so B will not do anything and then A will go alone and A will be killed so the idea of the two general problem mean if all the general for example like 2 general 3 general 4 general if they agree the same if they make the same decision they will win the city if they are not make the same decision they will some of them will be killed okay so in this case A will be killed because B did not receive the message តោះណាតោះឡើងហ្នឹងអាហ្នឹងដូច network handshake ចឹងបានន័យថាតោះតែវាមាន3 handshake ឧទាហរណ៍ថា sing act and act តោះពេលអានេះវាបាន sing act វាអត់ឃើញ act មកចុងក្រោយនេះអញ្ចឹងបើវាអត់ act ទេបានន័យថា A នេះវាច្បាស់ជាអត់ confirm ហើយបានន័យថាការដំបងវាចង់វាយមែនវាពិតតែចង់វាយមែនតែរួចតិចចុងបញ្ចប់វាអត់ confirm ហ្មងហ្នឹងតោះណាឧទាហរណ៍ថាតោះឥឡូវនាំគ្នាលេងកំពង់សោមហ៎អូអាមួយនោះថាអូខេទៅក៏តែតោះឯងទៅដែរហើយទៅអត់តោះទៅពេលហើយទៅអត់អានោះអត់ឆ្លើយឥឡូវសួរថាទៅអត់ចុះបើវាអត់ឆ្លើយហ្នឹងតោះណាអញ្ចឹងមានន័យថាអត់ទៅអញ្ចឹងបានន័យថា decision គឺអត់អាច happen បានទេនៅពេលដែលមនុស្សទាំងអស់អត់ agree យល់ទេហើយអាមូលហេតុហ្នឹងហើយដែលយើងហៅថា problem two general problem understand so in this case B will go to fight and A will not go to fight so A will lose and then we can say that A and B did not make an agreement okay they did not make an agreement to fight the city together when there is a network failure happen or some message is lost. Okay, so in this case the message lost at the end. So what happen if the message lost at the second? Like A want to attack, but B send okay I will attack, but the message is lost or capture or killed by the city. So will both the army go to attack or not? ចឹងមកថាអាករណីនេះបានថា message នេះវាបាត់តាំងពីអាទី2នេះតោះណាវាមិនមែនបាត់អាទី3ចុងក្រោយនេះទេតោះណាវាបាត់តាំងពីអាទី2នេះមានន័យថាអាមួយនេះថាជួយអញផងទៅ attack អីតោះដល់ពេលអាទី2នេះថាអូខេអញទៅ attack ដែរក៏តែ message នេះវាអត់មកដល់ទេសួរថាអាពីរនាក់ហ្នឹងទៅវាយអត់ទៅអត់អត់ទៅទេហ្នឹងហើយ so now General A want to attack but General B he want to attack too but the message is lost. So in this case the same thing, both general did not make an agreement, so they will not go to fight. Okay, so that we call two general problem. Okay, so now you know what is two general problem mean. So now let's see if the number of general is bigger than 2, like 3, 4, 5, 6, 7 or 10. Okay, so if the number is getting bigger, how do they talk to each other? Okay, so in this case we have a 3 general. So in that case we don't call a 2 general problem anymore. We call it Byzantine general problem because it is related to Byzantine Empire, and then the number of general is more than 2. Okay, so we call it Byzantine general problem. So we have, for example, we have 3 general, but suppose that one of the 3 is a failure, or we can call a failure, a traitor, or a malicious, something like that. For example, like we have 3 army, but one army is take money from the big city or the big government. Okay, for example, like we have 3 army. Okay, we have 3 army, 3 general. We have 3 general, but one general is not a good general. Okay, one general is taking money from the city. Okay, so now they want to talk to each other. The same thing, they want to talk to each other through the network. Okay, they need to talk through the network in order to attack. So this one need to talk like this, this one need to talk like this, and this one need to talk like this, this one need to talk like this. Okay, so they need to talk with each other in order to attack the city. But within the 3 general, one is not good. Okay, so normally the green one we call it an honest one. Okay, honest general, honest computer, honest node, something like that. But if the computer is not good, we call it malicious. Okay, malicious, or we call it failure. Normally you can see it F. So F means fail. Okay, faulty or failure, something like that. Okay, ចឹងបានន័យថាយើងមានមេតប3កុំតែក្នុងចំណោមមេតប3ហ្នឹងមួយក្បត់តើណាអាពីរវាល្អហើយតែមួយទៀតក្បត់ដោយសារវាស៊ីលុយគេតើណាចឹងទៅគឺ message ដែលវាផ្ញើមកហ្នឹងវាអាចជា message អត់ពិតប្រាកដទេ Okay, so if we have a 3 general and one of them could be traitor or malicious or faulty, we say it F. So F equal to 1, which means among 3 one of them is not good. Okay, and then N is the total number. So we have 3 army. For example, like the first general is a faulty or malicious. The first general he didn't say anything because he is faulty, and he sent the message. So the first column is the message that the first general sent to the second general, sent to the third general. Okay, so the first general sent to the second general that okay, tomorrow I want to attack, but he sent to another one, I don't go to attack, I will retreat. Okay, so when the 2 general receive this message, the 2 general need to send the message to the other one. For example, like he received the message attack, so which means he need to send attack to the first one, attack to the second one. Okay, but for the third one, he received the message retreat, so he will send retreat to the second one, retreat to the first one. Okay, and after that, what are the decision? So the decision is depend on the majority. So let's see this one. So this one received 2 attack and 1 retreat. So tomorrow he will go to attack. Okay, but the second one is a retreat, attack, retreat. So the majority of the message is retreat, so he will make decision retreat. Okay, and the first one is we don't care because they are the traitor or the malicious ones, the malicious general. Okay, so in the final decision we can see that the decision is not agree. They did not make a unique agreement. Okay, so the agreement is one is attack, one is retreat, and one is something we don't know. He can say attack or retreat, depend on him because he is the traitor. So finally, we don't know what are the decision to make the attack or not. And that is why we said that this is also a problem. We call it Byzantine general problem. Okay. Okay, I can explain a little bit again, summarize. For example, like now we have 3 army. Okay, we have 3 army. So we have a city that we want to attack. Okay. For example, like this is a malicious general. So this one is not a good general. Okay. So when he want to he sent this message to these people, said that okay, I want to attack. Okay. So this one receive one message, attack now. Okay. And then because he's malicious, he sent to the other one, I don't go to attack, I retreat. Okay. Because he's not a good general, he said to this person, I attack. He said to this general, I retreat. So when this general receive a message attack, so he mean that okay, now one person attack, so I want to help him, I want to attack too. Okay. So that's why he sent another message attack to this one. So this one now he received one message attack from the second general, and this one because he honest, he sent also attack message to this general. Okay. So now this general receive a retreat from this one, and then attack from this one. Okay. Understand? But this general is also honest. When he receive a message retreat, something like this, he send the message retreat to this one. Okay, I will not retreat. I will not attack because one of our friend will not go, so I will not go too. Okay, so this person will get the message retreat, and he will send retreat back to this one. So this one also receive a message retreat. Okay. Okay, so let's say how many that we get. Cú cho cú lắng trong vậy luôn này. So retreat, and then yeah, he will retreat also because he sent the message retreat to both of them, so he will retreat also. So finally, this general, in conclusion, he has a retreat more than attack, so the final decision is retreat. Okay, but this general, he has a accept more attack more than retreat, so his final decision is attack. Okay. But this one we don't care because he malicious, so it can be attack or retreat. It doesn't matter because he's not a good person. Okay. So now tomorrow what will happen? Tomorrow what will happen? Tomorrow which general go to attack? For example, this one is A, this one is B, this one is C. So who can tell me tomorrow which general go to attack Empire, the Byzantine Empire city? ចឹងក្នុងចំណោមមេតប3មានមេតបមួយក្បត់វាផ្ញើសារមួយទៅថាវាយផ្ញើសារទៅមួយទៀតអត់តោះណាដល់ពេលផ្ញើចុះផ្ញើឡើងអានេះវាបាន3 message 2 message វាថាអត់វាយទេ1 message ថាវាយអញ្ចឹងវាអត់ទៅវាយដោយសារអីដោយសារតែ message អត់វាយនោះវាច្រើនជាង message ទៅវាយបានន័យថាតបអ្នកទៅវាយហ្នឹងគឺតិចជាងតោះណាតោះតែវាទៅទាំង3នាក់បានវាទៅបើវាទៅតែ2នាក់ក៏វាអត់ទៅដែរតោះណាដល់ពេលមិន3នាក់បានទៅឯងគឺ majority បានន័យថាបើសិនជាមាន2នាក់ទៅគឺវាទៅហើយតែតទៅពេលអានេះគឺវាមានតែម្នាក់វាដែលទៅអា2នាក់ទៀតវាអត់ទៅអញ្ចឹងណាតពេលអានេះគឺមាន2នាក់ទៅហើយមួយអត់ទៅអញ្ចឹងវាច្បាស់ជាទៅហើយតណាតែឥឡូវសំណួរសួរថាតើស្អែកឡើងប្រហែលអ្នកទៅវាយអា city មួយនេះ Which general go to fight the city? Okay, B so yeah, so B will go alone because B is honest and he's received a 2 attack, so B will go alone. Okay. C will not go because C will retreat. C will stay at home. Okay, and A will not go too because A is malicious. It belongs to this empire. So when B go alone, this empire kill B. Okay, so now B is killed. This is a malicious, and then this is a retreat. So the system is not make an agreement. Okay, so that's why we call it Byzantine general problem. So when there is a 3 computer, and if one computer among the 3 is not good, the system will not make an agreement. Okay, understand? ចឹងបានន័យថា Byzantine general problem នោះមានន័យថាម៉េចបើយើងមានកុំព្យូទ័រតែ3គ្រឿងឯងហើយកុំព្យូទ័រនោះវានិយាយគ្នាទៅវិញទៅមកអញ្ចឹងណាកុំតែមានអាកុំព្យូទ័រមួយត្រូវបាន hacker វា hack យកបាត់ហើយតោះណាអញ្ចឹងក្នុងចំណោម3កុំព្យូទ័របើមានកុំព្យូទ័រមួយណាដែលវាអត់ល្អគឺវាអត់អាច system របស់យើងហ្នឹងគឺនិយាយគ្នាអត់ចោះសម្រងគ្នាដោយសារតែមានអាមួយទៅវាយអាមួយអត់ទៅវាយអញ្ចឹងទៅតោះណាហើយអាករណីបែបហ្នឹងឯងដែលយើងឲ្យឈ្មោះថា Byzantine general problem យល់ទេតោះណា understand? So now the question is, how many computer do we need in order to tolerate F computer that is malicious or have been hacked, have been compromised or have been down or something like that? Okay. អញ្ចឹងសំណួរសួរថាតើយើងត្រូវការប្រមាណកុំព្យូទ័រដើម្បីទប់ទល់ជាមួយនឹងអាកុំព្យូទ័រដែលវាអាក្រក់នេះយើងមានរូបមន្តអីអត់ តោះណាព្រោះអីបើសិនជា3កុំព្យូទ័របានន័យថា3កុំព្យូទ័រតែមានកុំព្យូទ័រមួយខូចគឺ system យើង down បណ្ដោយគឺអត់អាចទប់ទល់ជាមួយនឹងកុំព្យូទ័រមួយនឹងខូចទេតោះតែកុំព្យូទ័រយើងមាន4គ្រឿងបានអាចទប់ទល់ជាមួយនឹងមួយនឹងកើតតោះណាបើមានតែ3គ្រឿងចឹងទេទប់ទល់អត់កើតទេអូខេអញ្ចឹងសំណួរសួរថាតើកុំព្យូទ័រយើងត្រូវការប្រមាណដើម្បីទប់ទល់ជាមួយនឹង faulty នឹងកើតអូខេ So in order for our system to be availability បានន័យថា available all the time or our system is fault tolerant it means tolerate to fault even if it is fault it's still functioning so how many computer do we need okay how many n do we need so n is the number of a total computer and f is the number of a malicious computer or the computer that has been compromised or the computer that is down because of the network failure something like that okay so the question is how many computer do we need so up to f general might behave maliciously that means F represent the computer that is not functioning normally. It could be someone hacked, it could be compromised, it could be down because of some other reason. And honest general don't know who the malicious one are. So which means if we have a 3 computer like this, we don't know which one is the one who are malicious. Okay, so we don't know because all the computer look the same. The malicious general may collude, so that means the malicious computer may send malicious information to the other computer, like one is attacked, the other one is not attacked, something like that. And an honest general must agree on the plan. So an honest general, if they see the plan is retreat, it will retreat. If it see the plan is attack, it will attack. So the general, the honest general must agree with the plan that it receive. Okay. So if the majority of the message is attack, it will go to attack and it will die alone. If the majority of the message is retreat, it will retreat. Okay. So those are the property of those examples. So normally in the computer science, there's a researcher try to solve this problem and he come up with an idea or formula, which means 3f plus 1 can tolerate f malicious problem. Okay, so you can go to read the paper if you want. And then we will see an example here. So when he do the research, he come up with the number in order to tolerate f computer, we need to have 3f plus 1 computer. So n is equal to 3f plus 1. Okay. So for example, like if we have one malicious computer, what are the total number of the computer that we need? ចឹងឧទាហរណ៍ថាគេរកឃើញរូបមន្តមួយបានន័យថាដើម្បីទប់ទល់ជាមួយនឹងកុំព្យូទ័រអាក្រក់ហ្នឹងគឺតើតា number កុំព្យូទ័រហ្នឹងវាស្មើនឹង 3f បូក 1 ដែរ f នេះគឺជា number របស់កុំព្យូទ័រដែលវាខូចហើយនឹងអា n នេះគឺជា number of កុំព្យូទ័រទាំងអស់តោះណាឥឡូវឧទាហរណ៍ថាតើនៅពេលដែលមានកុំព្យូទ័រមួយខូចមួយសួរថាយើងត្រូវការកុំព្យូទ័រប៉ុន្មានគ្រឿង So what are the number of n when there is one computer act maliciously how many computer do we need ប្រហែល 4 ត្រូវទេដោយសារមួយដាក់ចូលទៅចេញ4ហើយ So now if there is a 2 computer has been compromised by the hacker what are the computer that we need in order to make our system availability or tolerant ប្រហែលបានន័យថាក្នុងចំណោមពេលដែលយើងចង់ build system ហ្នឹងទៅយើងចង់ឲ្យ system យើងបានន័យថាបើទោះបីជាមានកុំព្យូទ័រ2ខូចក៏កុំព្យូទ័រយើងនៅតែដំណើរការដែរអញ្ចឹងសួរថាតើយើងត្រូវតែឡើងកុំព្យូទ័រ server ប្រហែលគ្រឿង 7 okay so if we want to withstand 2 computer compromise or hardware failure or something like that we need 7 computer okay 7 server so if 7 computer if 2 is full we still have 5 and then if we have 5 computer the system is still running properly there is no crash no down or whatever okay and we can add on for example like if I have 7 computer failure how many computer do I need បានន័យថាឥឡូវយើងចង់ឲ្យអា system យើងមកបើទោះបីជា7កុំព្យូទ័រខូចក៏នៅតែដើរយើងត្រូវការកុំព្យូទ័រសរុបប្រហែល 22 okay so you can see that the number of the total computer is increasing when your system want to be tolerate with much bigger faulty okay so if your computer want to tolerate a lot of fault when the fault increase the total number of computer need to be increased too okay so if the total number of computer is increased which means you need to pay a lot of money too okay because you need to maintain a lot of computer but your system is also good because even if there is 7 computer failure your system is still running understand this formula អញ្ចឹងរូបមន្តនេះគឺចង់និយាយថាបើទោះបីជាកុំព្យូទ័រនោះវាខូចមួយគ្រឿងខូចពីរគ្រឿងខូច7គ្រឿងក៏ដោយក៏កុំព្យូទ័រយើងនៅតែដំណើរការដែរតោះណាបើសិនជាចង់ឲ្យកុំព្យូទ័រយើងដំណើរការតើតែកុំព្យូទ័រយើងមាន22គ្រឿងតោះណា22គ្រឿងនោះវាទប់បានតែ7ទេតោះណាបើសិនជា8គ្រឿងមកដល់គឺអា22នេះក៏ទប់អត់ជាប់ដែរអញ្ចឹងវាត្រូវតែឡើងទៀតដែរយល់ទេអញ្ចឹងបានន័យថា22 or more understand so let's summarize our lesson what does fault tolerant mean fault tolerant mean we need to do something even if there is a faulty or computer compromise, our computer still functioning. So that is called tolerant. Okay, fault tolerant. Fault, even if it is fault, it is still tolerant. So the formula is we need at least 3F plus 1 total computer in order to deal with F failure. Okay, so that is the formula. And then the last one, the key takeaway. Node need to communicate with each other. So you can see that if we have a lot of computer, like a lot of computer, don't save here. Okay. So for example, like if we have 5 computer, 1, 2, 3, 4, 5, something like this. Okay. So if maybe I can write in a pentagon style. So if you have 5 computer in a distributed system, those computers need to talk to each other. Okay. So node need to communicate with each other. So you can see that now, if I have 5 computers, those computers need to talk to each other. So you can see that we have communication between this computer like this. See? So when we have 5 computers, how many communication do we have? បានន័យថាបើសិនយើងមាន5កុំព្យូទ័រសួរថាអា communication យើងមានប្រមាណមានប្រមាណ if I have only 3 computer if I have only 3 computer so those 3 computer need to communicate like this so this one need to talk to this one need to talk to this one and this one and then this one need to talk to this one and this one and then this one need to talk to this one and this one okay you can see that when you have 3 computer you have 6 communication but if you have a 5 computer you this one need to talk to all the 4 and then this one needs also to talk to all the 4 this one also need to talk to all the 4 something like that okay so remember that when the computer is getting bigger the number of communication is also getting bigger so we say that this is the cost of communication okay cost of communicationចឹងត្រូវចាំថានៅពេលដែលកុំព្យូទ័រយើងមានកាន់តែច្រើនទៅអាកុំព្យូទ័រនោះវាត្រូវការនិយាយគ្នាអញ្ចឹងបើវាត្រូវការនិយាយគ្នាមានន័យថាម៉េចអា cost នោះភាគច្រើនគឺយើងសំដៅទៅលើ speed លើ memory លើអីអស់ហ្នឹងបានន័យថាគឺវា cost អាការដែលយើងត្រូវការនិយាយគ្នាហ្នឹងគឺវាត្រូវស៊ីពេលច្រើនហើយតោះនេះបានថា cost ហ្នឹងគឺវា increase ដែរហ្នឹងហើយបានខ្ញុំដាក់កន្លែង key takeaway នេះ so node need to communicate with each other so whenever the number of the computer increase the cost of the communication also increase okay and the other thing is majority idea is a global decision. So when you have a lot of computer, for example, like you have a 7 computer, 22 computer, 4 computer, 5 computer, something like that, the majority of the decision is the decision of the whole system. Okay, we count on the majority. And how do we count on the majority? We need to do a method called voting or election. Okay, so we need to elect. And then if the majority of the election say something like attack or retreat, we need to approve like that. Okay. So in order for the distributed system to make some decision, they need an election or they need a voting system. Understand? Communication come with cost. So sometimes when there's a lot of communication like this, people try to find the solution to those problems by choosing a centralized way, for example, like by choosing a leadership way, for example, like if we want to make a decision and then there's a lot of computer like this, I don't want all the computer to talk to each other. We need to choose only one computer to be the leader. Okay, for example, like now we have a 60 students. Okay, so now we have 60 students, just like we have a 60 computer. Okay. But if we allow the 60 computer to talk to each other, the communication is a lot. That's why sometimes people choose a centralized way, which means they choose one people among those people to become a leader. Okay. a leader. And then those kind of system, we call it leader based. So everyone need to listen to the leader. Okay. For example, like now, even if we have 60 computer, but everyone don't make a decision. The decision is made by the leader. Okay. So how do we choose a leader? So we choose a leader by voting, okay, or by election. So now if after we have vote someone to become a leader, we have a leader, and then if the leader said attack, all the system need to attack together. Okay. If the leader said, okay, now we retreat. Okay, so now all the system need to retreat with each other. So in this case, we only have n communication. So if there is n computer, the leader need only for n-1 communication. So we don't have a n square communication. Okay. So this is by choosing the leader, we can reduce the cost of communication. Okay. But we can reduce the cost of communication. But what is the problem? Anybody can see the problem. So now if you choose the leader, you can slow down the cost of the communication. Okay, the communication go down. But what are the problem? Communication. What are the problem? ចឹងមានន័យថាបើសិនកុំព្យូទ័រមានកាន់តែច្រើនទៅហើយវាត្រូវការនិយាយគ្នាបើយើងមាន n កុំព្យូទ័រអានិយាយគ្នានោះគឺ n ការ៉េបានន័យថាវាត្រូវនិយាយគ្នាទៅវិញទៅមកនោះអញ្ចឹងអាចំនួននៃការនិយាយគឺ n ការ៉េតោះណាតែដើម្បីកាត់បន្ថយអាការ communication នោះឲ្យវានៅសល់ត្រឹម n ឬក៏ n ដក1គឺក្នុងចំណោមកុំព្យូទ័រទាំងអស់នោះគឺគេរើស leader មួយហើយតទៅពេល leader ថាម៉េចអាកូនចៅត្រូវធ្វើតាមហើយតោះណាបើ leader ប្រាប់ថាទៅវាយទាំងអស់គ្នាបើថាអត់ទៅវាយទាំងអស់គ្នាអញ្ចឹងអាហ្នឹងវាធ្វើឲ្យ communication ខុសចុះមែនក៏តែសួរថាវាបង្កើតបញ្ហាអីកើតឡើងវិញមានអ្នកគេដឹងអត់
បើសិនជា leader faulty គឺចប់
Okay, so that is the problem. So when the leader become faulty, okay, so when the leader become faulty, you have 60 people but only one people bad and that bad person become a leader, your whole group will go failure. Okay, for example, like your whole group will make a wrong decision. So the problem is when the leader is fall, your system will go down, and this is the problem of the centralized because you can see that even if you have 60 computer, but the way that you make decision is centralized on one single computer. So in the distributed system, we say this one is a single point of failure. Okay, single point of failure. So remember that some distributed system, they say that, okay, my system is distributed. I have 60 copy of the data. I have 60 computer. But in reality, those 60 computer is only depend on one leader or maybe 2 leader or maybe 3 leaders. Okay, so in this case, it is not truly a distributed system because it is still has some failure point. We call it single point of failure because our leader is very too small. If it is one, it's single. Okay, single point of failure. And so whenever people say that, okay, my system is distributed system, don't trust them. Okay, see how they make decision. How those 60 computer make decision. If they make decision based on the leader, why they choose the leader approach? Because they don't want the communication to be a lot. Okay, they want to consume less time, so they choose one leader. So that means the system running very fast, but it might fall because of the leader. Okay, so that's why there are a lot of this decision making algorithm. We call it consensus algorithm. So some approach we use the other approach. So those approach we will learn in chapter 5, like puzzle, zookeeper, RAF is also a consensus algorithm. And then within week 3, week 7, week 8, week 9, we also learn proof of work is also a consensus algorithm. Proof of stake is also consensus algorithm. And Hyperledger, they use a RAF consensus algorithm, something like that. Okay. So in order to make decision, there are a lot of algorithms that people have created, and we will learn in the next week. Because if we choose only one leader like this, the system is not fault tolerant. Okay. So in order to build a fault tolerant system, normally we say that I want to build a Byzantine fault tolerant system. Okay, so normally you will see the word BFT. So FT is fault tolerant. Okay, B is Byzantine. So how do you build a Byzantine fault tolerant system if you have 60 computer? Okay, if you have one computer to be a leader, this is not a Byzantine fault tolerant system. Okay, so how do you design a system in order for your 60 computer to become Byzantine fault tolerant system? So in this case, we need to know what are the algorithm that people create in order to make decision. Okay, decision. So how do you make decision? What are the rules that you need to take? Okay, so those algorithm we call it consensus algorithm. Okay, consensus algorithm. And then we will talk in the next chapter. ចឹងបានន័យថា system មួយនៅពេលមានកុំព្យូទ័រច្រើនវាត្រូវនិយាយគ្នាហើយអានិយាយគ្នាហ្នឹងវាត្រូវបង្កើតច្បាប់តោះណាអាច្បាប់អាកូដដែលយើងទៅសេហ្នឹងយើងឲ្យឈ្មោះថា algo ឬមួយក៏ decision ហើយតោះណាហើយពាក្យបច្ចេកទេសគេហៅថា consensus algorithm គឺជាក្បួនច្បាប់ដែលឲ្យកុំព្យូទ័រជាច្រើនហ្នឹងវានិយាយគ្នាហើយវា make decision ពីព្រោះបើអត់មានក្បួនច្បាប់ហ្នឹងទេបើយកតែមួយមកធ្វើ leader ទេគឺតែមួយនឹងខូច system យើងត្រូវ down ហើយតោះណាអញ្ចឹងមនុស្សបានបង្កើត consensus algorithm ច្រើនហើយយើងនឹងរៀនវាម្ដងមួយចង់ដឹងថាចាំមើលអាមួយណាវាមិនខ្លះតោះSo today you learn about the computer could be fault, could be compromised, could be down by hardware, network, software, something like that. You know that if you have two computers, there might be problem of the network loss because the message may be lost. And if you have more than two generals, some general may be act maliciously. So that's why in next week we will learn how do people create a system that can tolerate those kind of fault, okay? And then those algorithm we call it consensus algorithm, okay? តោះចឹងយើងជួបគ្នាអាទិត្យក្រោយទៀតហើយយើងនឹងរៀនទឹកក្រោយថ្ងៃពហុយើងអាចចាប់ផ្ដើមប្រើតាក់ទងជាមួយនឹងរឿង consensus algorithm មានន័យថាកុំព្យូទ័រហ្នឹងពេលដែលវាមានច្រើនវាច្បាស់ជាអាខ្លះត្រូវបានគេ hack អាខ្លះវាខូចអាខ្លះវាអីហើយអញ្ចឹងតើគេត្រូវតែសេកូដមិនដើម្បីឲ្យកុំព្យូទ័រហ្នឹងវានិយាយគ្នាទៅវាអាច make decision រួមគ្នាបានបើទោះបីជាមានកុំព្យូទ័រខ្លះវាខូចក៏ដោយតោះណាហើយអាវិធីសាស្ត្រនៃការទៅសេកូដ make decision ហ្នឹងយើងហៅថា consensus algorithm តោះអាហ្នឹងយើងនឹងរៀននៅមេរៀនក្រោយទៀត Okay, question. So today we talk about the last chapter of the clock, and then we also talk about the fault tolerance, like computer could fall, and then there's a two general problem, Byzantine general problem, and then the solution to solve those problems is the next chapter, is the consensus problem. Okay, the consensus algorithm is the algorithm to solve the Byzantine problem or two general problem. Understand? Question. Means what? So if no question, bye bye. If have question, you can ask.
Okay.
ឡើងហើយសួរមក
នៅពេលដែលយើងមានអា consistent algorithm ហ្នឹងឯងយើងត្រូវការalgorithm មួយណាដែលត្រូវ control នៅ connection ហ្នឹងទៀតអត់
អត់ត្រូវការ So the question is if we have one algorithm, do we need another algorithm? No. All the computer needs to install those algorithm. Okay. So for example, like all the students need to agree in the classroom rule. So there's no, for example, some of the system can choose some leader like 2, 3, 4, 5. Some of the system don't have leader. They all become the leader, something like that. But all the computer need to have the same rule. Like they need to install those kind of software, and when they communicate with each other, they use that rule to validate their decision. Okay. So in that case, we don't need another algorithm. We only need one algorithm, and all the computer need to install that algorithm. But remember that there is not only one algorithm. There are a lot of algorithm and different system using different kind of algorithm. អញ្ចឹងនៅពេលដែលយើងមាន algorithm មួយប្រៀបដូចជាយើងមានច្បាប់មួយអញ្ចឹងហើយរួចទៅកុំព្យូទ័រទាំងអស់វាត្រូវ install អាច្បាប់ហ្នឹងគ្រប់កុំព្យូទ័រណាក៏ត្រូវមានអាច្បាប់មួយហ្នឹងដែរតើពេលវាចង់ make decision វាយកច្បាប់មកមើលបានថាច្បាប់ទី1និយាយថាមកច្បាប់ទី2និយាយថាមកអញ្ចឹងតើពេលវាមើលច្បាប់ចាប់ហើយវា make decision ហើយតើណាហើយទោះបីជាក្នុងចំណោមកុំព្យូទ័រទាំងអស់ហ្នឹងមានអាណាខូចក៏ដោយដោយសារតែ majority នៃកុំព្យូទ័រទាំងអស់ហ្នឹងវា make decision អញ្ចឹងយើងយក majority ជា goal ហើយយើងមានតែ algorithm ហ្នឹងមួយគឺរួចខ្លួនហើយតែសំណួរមួយទៀតសួរថាតើ algorithm ហ្នឹងមានតែមួយឬមួយក៏មិនទេបានន័យថាមិនមែនមានតែមួយទេវាមានច្រើនណា algorithm សម្រាប់ make decision ហ្នឹងអញ្ចឹងយើងនឹងរៀននៅមេរៀនបន្តទៀតយើងនឹងឃើញប្រភេទវាច្រើនហើយ system ខ្លះគេប្រើអានេះ system ខ្លះគេប្រើអានោះទៅតាមប្រភេទ system អញ្ចឹងទៅអូខេតែសំខាន់គឺកុំព្យូទ័រទាំងអស់គឺមាន algorithm ដូចគ្នាទាំងអស់ហើយ algorithm ហ្នឹងយើងហៅថា consensus algorithm តោះណាតោះណាOkay, so maybe Thursday we start to learn some kind of algorithm, and you will know that those computers need to talk to each other. So how can they talk to each other? It's our chapter 2. Okay, they use gRPC, they use RPC, so they need to talk to each other. That's why we need some talking technology. And after that, we need to select some leader. Okay, so that's why the leader need to send a heartbeat message to the follower. So in the system that has leader, our last example is sending heartbeat message. It is relevant. Okay, so leader need to stay alive all the time, and if one leader die, we need to select another leader, something like that. Okay, so that also a type of consensus algorithm. And the other consensus algorithm, no leader at all. So every computer become a leader. So in that case, we don't need heartbeat information. Okay, so you can see that when I talk like this, there is a lot of algorithm, and then each algorithm is working differently. Okay. ចឹងដោយថាខ្ញុំនិយាយមិញវាមាន algorithm ច្រើនណា algorithm ខ្លះ computer ច្រើនវាត្រូវការនិយាយគ្នាអញ្ចឹងយើងប្រើមេរៀន RPC GRPC ហ្នឹងគឺយកមកប្រើហើយបន្តមកទៀតconsensus ខ្លះវាត្រូវការ leader ដូចថាមួយ leader 5 leader 24 leader អញ្ចឹងណាអញ្ចឹង leader ហ្នឹងវាត្រូវ send heartbeat ឲ្យ client របស់វាដូចបច្ចេកបេះដូងដែលយើងរៀនអាទិត្យមុនហ្នឹងតទៅពេលconsensus ខ្លះអត់មាន leader ហ្មងប៉ុន្តែទាំងអស់ហ្នឹងគឺគ្មាន leader គឺស្មើភាពគ្នាហើយវានិយាយគ្នាទៅវិញទៅមកអញ្ចឹងទៅតោះណាអញ្ចឹងចាប់ពីអាទិត្យក្រោយទៅយើងនឹងឃើញប្រភេទខុសៗគ្នាទាំងអស់ហ្នឹងហើយអូខេOkay, so let's finish our course today and let's meet each other again on Thursday, and we will talk about the consensus algorithm. Bye bye. Bye bye.